When Apollo 11 successfully landed humans on the moon in 1969, astronauts Neil Armstrong and Buzz Aldrin experienced many firsts, including eating food on the lunar surface. Among the items carried with them were small, preserved portions of food designed for space travel, including bacon cubes. These were part of specially prepared meals that could be easily stored, transported, and consumed in a low-gravity environment. The bacon was cooked, processed, and packaged to ensure it remained safe and edible during the mission. Eating on the moon was not just about nourishment, but also about testing how humans could perform basic tasks in an entirely new environment. Every action, from opening a package to handling food, required careful planning. The presence of familiar foods like bacon helped provide a sense of normalcy during a mission that was otherwise extraordinary. This moment represented a small but meaningful step in human space exploration, showing that even on another world, elements of everyday life could be carried along. If you tried to reach the moon by car, driving continuously at a steady highway speed of 100 kilometers per hour, the journey would take far longer than most people expect. The average distance to the moon is about 384,000 kilometers, which means the trip would last roughly 161 days without stopping. That is over 5 months of constant travel, day and night, with no breaks. Extending that same idea even further reveals just how vast space really is. If you attempted to drive to the sun at the same speed, the journey would take around 171 years. That is longer than a human lifetime, just to reach the closest star to Earth. These comparisons help translate astronomical distances into something more relatable, even though the reality is still difficult to fully grasp. Space is not just big, it is overwhelmingly vast in a way that challenges everyday understanding. What feels like a simple trip on Earth becomes a journey that spans generations when applied to space. And when we try to shrink these distances into something more familiar, the scale becomes even more striking. To better understand the size of our solar system, imagine scaling the sun down to the size of a basketball. In this model, the Earth would shrink to something as small as a grain of sand. But what makes this comparison even more powerful is the distance between them. That tiny grain of sand would need to be placed about 27 meters away from the basketball-sized sun to represent the real distance between Earth and the Sunday. This means that even at a drastically reduced scale, most of the solar system is still empty space. The planets would be scattered far apart, with vast gaps between them, emphasizing how spread out everything truly is. It also shows how small the Earth is compared to the Sun, not just in size, but in significance within the system. Despite being our entire world, it becomes almost insignificant when placed into this perspective. These kinds of models help bridge the gap between human intuition and cosmic reality, making it easier to visualize something that is otherwise too large to comprehend. And yet, even this solar system is only a tiny part of something far greater. Beyond our solar system lies the Milky Way galaxy, an immense structure that contains hundreds of billions of stars, including our own Sunday. The galaxy itself stretches across about 100,000 light-years from one side to the other. A light-year is the distance light travels in a year, moving at a speed of about 300,000 kilometers per second. Even at that incredible speed, light would take 100,000 years to cross the entire galaxy. From our position within the Milky Way, the center lies about 25,000 light-years away. This means that the light we see coming from the galactic center today actually began its journey 25,000 years ago. It is a reminder that when we look into space, we are also looking back in time. The scale of the Milky Way places our solar system into a much larger context, showing that even the vast distances within our own system are small compared to the size of the galaxy we inhabit. Far beyond our galaxy, at a scale that is almost impossible to fully imagine, lies one of the largest known structures in the universe, the Hercules Corona Borealis Great Wall. This immense formation stretches across an estimated 10 billion light-years, making it one of the most massive structures ever observed. To put that into perspective, a single light-year is the distance light travels in 1 year, and even that is already beyond ordinary comprehension. Expanding that to billions of light-years means this structure spans a significant portion of the observable universe. It is made up of clusters of galaxies, bound together by gravity and arranged in a pattern that forms a kind of cosmic wall. Discoveries like this challenge earlier assumptions about how matter is distributed across the universe, suggesting that large-scale structures can be far more extensive than once thought. The sheer size of this formation raises questions about how such structures form and evolve over time. It is not something that can be seen directly with the eye, but rather detected through patterns in distant observations. And while this structure exists on an almost unimaginable scale, even within our own cosmic neighborhood, there are events unfolding that will reshape galaxies themselves. Closer to home, on a scale that is still vast but more directly relevant to our place in the universe, the Andromeda Galaxy is moving steadily toward the Milky Way. Located about 2.5 million light-years away, Andromeda is the nearest large galaxy to our own, and it is on a collision course that will unfold over billions of years. Scientists estimate that in roughly 4.5 billion years, the two galaxies will begin to merge. This does not mean a sudden crash in the way we might imagine, but rather a gradual interaction where gravitational forces pull stars, gas, and dust into new configurations. Because of the immense distances between individual stars, direct collisions are unlikely, but the overall structure of both galaxies will change dramatically. Over time, they will combine to form a new, larger galaxy, often referred to as a merged elliptical system. This event is a natural part of how galaxies evolve, driven by gravity over long timescales. It is a reminder that even the largest structures we observe are not permanent, but constantly changing, shaped by forces that operate across billions of years. If you tried to reach the moon by car, driving continuously at a steady highway speed of 100 kilometers per hour, the journey would take far longer than most people expect. The average distance to the moon is about 384,000 kilometers, which means the trip would last roughly 161 days without stopping. That is over 5 months of constant travel, day and night, with no breaks. Extending that same idea even further reveals just how vast space really is. If you attempted to drive to the sun at the same speed, the journey would take around 171 years. That is longer than a human lifetime, just to reach the closest star to Earth. These comparisons help translate astronomical distances into something more relatable, even though the reality is still difficult to fully grasp. Space is not just big, it is overwhelmingly vast in a way that challenges everyday understanding. What feels like a simple trip on Earth becomes a journey that spans generations when applied to space. And when we try to shrink these distances into something more familiar, the scale becomes even more striking. To better understand the size of our solar system, imagine scaling the sun down to the size of a basketball. In this model, the Earth would shrink to something as small as a grain of sand. But what makes this comparison even more powerful is the distance between them. That tiny grain of sand would need to be placed about 27 meters away from the basketball-sized sun to represent the real distance between Earth and the Sunday. This means that even at a drastically reduced scale, most of the solar system is still empty space. The planets would be scattered far apart, with vast gaps between them, emphasizing how spread out everything truly is. It also shows how small the Earth is compared to the Sun, not just in size but in significance within the system. Despite being our entire world, it becomes almost insignificant when placed into this perspective. These kinds of models help bridge the gap between human intuition and cosmic reality, making it easier to visualize something that is otherwise too large to comprehend. And yet, even this solar system is only a tiny part of something far greater. Beyond our solar system lies the Milky Way galaxy, an immense structure that contains hundreds of billions of stars, including our own Sunday. The galaxy itself stretches across about 100,000 light-years from one side to the other. A light-year is the distance light travels in a year, moving at a speed of about 300,000 kilometers per second. Even at that incredible speed, light would take 100,000 years to cross the entire galaxy. From our position within the Milky Way, the center lies about 25,000 light-years away. This means that the light we see coming from the galactic center today actually began its journey 25,000 years ago. It is a reminder that when we look into space, we are also looking back in time. The scale of the Milky Way places our solar system into a much larger context, showing that even the vast distances within our own system are small compared to the size of the galaxy we inhabit. Not every planet in the universe orbits a star. Some are cast out entirely, becoming what astronomers call rogue planets, worlds that drift alone through interstellar space. These planets are thought to form in normal star systems, much like Earth or Jupiter, but are later ejected due to gravitational interactions, often during the chaotic early stages of planetary formation. A close encounter with a larger planet or shifting orbital dynamics can fling them outward with enough force to escape their star's gravity completely. Once expelled, they begin a silent journey through the vast darkness between stars, with no sunlight to warm them. Many of these worlds are believed to be extremely cold, with surface temperatures dropping far below freezing, while others, especially larger gas giants, may retain some internal heat. Despite their isolation, scientists estimate there could be billions of rogue planets in our galaxy alone, possibly even outnumbering the stars themselves. Detecting them is difficult because they emit little to no light, but astronomers have identified some through gravitational effects and faint infrared signatures. These wandering planets challenge the traditional idea that worlds must orbit stars, showing that planetary systems can be far more dynamic and unstable than they appear. And while these planets drift through what seems like silent emptiness, space itself is not as quiet as it might seem. Although space is often described as silent, this is only true in a specific sense. In the vacuum of space, there is no air for sound waves to travel through, meaning that traditional sound, as we experience it on Earth, cannot exist. However, space is not completely empty. It contains charged particles, magnetic fields, and plasma, an energetic state of matter made up of ionized gas. Within these environments, waves can still form and travel, not as sound in the usual sense, but as vibrations in plasma. Instruments used by space agencies, including those operated by NASA, have detected these plasma waves and converted them into audio signals that humans can hear. When translated into sound, these waves reveal a range of eerie tones, hums, and pulses. The sun, for example, produces intense activity that generates vibrations in its surrounding plasma, creating what can be described as a continuous roar when converted into audio form. These sounds are not heard directly in space, but they represent real physical processes happening in environments far beyond Earth. They provide insight into the dynamic and active nature of space, showing that even in apparent emptiness, there is constant movement and energy. And understanding how these waves behave leads to a clearer picture of where sound can and cannot exist beyond our planet. Sound, as we know it, depends on a medium to travel through, such as air, water, or solid material. It moves as vibrations that pass from one particle to another, carrying energy through that medium. In the vacuum of space, where there are almost no particles, this process cannot occur, which is why space is often considered silent. However, this silence is not absolute. In regions where matter is present, such as gas clouds or plasma fields, sound-like waves can still propagate. These environments, while extremely thin compared to Earth's atmosphere, contain enough particles to allow vibrations to move through them. In massive gas clouds found between stars, for instance, pressure waves can form and travel, though at frequencies far too low for human ears to detect without conversion. Similarly, in plasma, electromagnetic interactions allow waves to move in ways that resemble sound transmission. These processes are fundamentally different from how sound behaves on Earth, but they follow similar principles of energy transfer through a medium. This means that while the vast emptiness between stars remains silent, certain regions of space are filled with subtle forms of motion and vibration. It is a reminder that space is not a uniform void, but a complex environment where different physical conditions create different possibilities for how energy moves and interacts. Not all planetary systems resemble our own. Among the most extreme examples discovered are what astronomers call hot Jupiters, gas giant planets that orbit incredibly close to their parent stars. Unlike Jupiter in our solar system, which takes nearly 12 years to complete one orbit, these planets can circle their stars in less than a single Earth day. This proximity exposes them to intense radiation and heat, often raising their atmospheric temperatures to well over 1,000 degrees Celsius. Under such extreme conditions, the chemistry of their atmospheres becomes unusual. Metals that would normally exist as solids on Earth, such as iron, can vaporize into gas and then condense into droplets, effectively creating clouds that rain molten metal. These planets are often tidally locked, meaning one side constantly faces the star while the other remains in darkness, producing dramatic temperature differences across their surfaces. Strong winds can sweep material from the intensely heated side to the cooler side, creating violent and dynamic weather systems. The existence of hot Jupiters challenged earlier models of planetary formation, suggesting that planets can migrate inward after forming farther away. They reveal that planetary systems can be far more diverse and extreme than once imagined. And while these worlds demonstrate the unusual outcomes of planetary evolution, the structure of the universe itself reveals patterns on an even larger scale. On the largest observable scales, the universe is not randomly scattered, but organized into a vast structure known as the cosmic web. This immense network is composed of filaments of galaxies and dark matter that stretch across billions of light years, connecting clusters of galaxies like threads in a three-dimensional web. Between these filaments lie enormous voids, regions with relatively little matter. The structure resembles a neural network in appearance, with dense nodes connected by long, thin strands. Dark matter plays a crucial role in shaping this web, acting as a gravitational framework that pulls visible matter into place. Over billions of years, gravity has drawn gas and galaxies along these filaments, forming the large-scale structure we observe today. This arrangement was revealed through detailed surveys of galaxy distributions and computer simulations of cosmic evolution. The cosmic web shows that the universe has an underlying order, even at the largest scales, governed by gravity and the distribution of matter. It is a pattern so vast that it extends across the entire observable universe, linking galaxies into a single interconnected system. And within this immense structure, individual objects can still display behavior that pushes the limits of physics. Among the most extreme objects known are pulsars, rapidly rotating remnants of massive stars that have collapsed into dense neutron stars. One of the fastest known examples is PSRJ 1748-2446 AD, a pulsar that spins at an astonishing rate of 716 times per second. This means that a point on its equator is moving at nearly a quarter of the speed of light, approaching about 24% of that ultimate cosmic speed limit. Despite its small size, typically only about 20 kilometers in diameter, a neutron star contains more mass than the Sun, resulting in incredibly strong gravity. The rapid rotation of a pulsar like this generates intense magnetic fields and beams of radiation that sweep through space like a lighthouse. As these beams pass Earth, they can be detected as regular pulses, giving pulsars their name. The stability of these pulses makes them some of the most precise natural clocks in the universe. However, spinning this fast also pushes the limits of what the star structure can withstand, as any faster rotation could cause it to break apart. Objects like this demonstrate how extreme conditions in the universe can produce phenomena that challenge our understanding of physics, revealing the incredible range of possibilities that exist beyond our planet. In the large-scale structure of the universe, galaxies are typically found clustered together along vast filaments, forming part of the cosmic web. However, there are also enormous regions where very little exists, known as cosmic voids. One of the most striking examples is the Boötes void, a region of space spanning roughly 330 million light-years across that contains an unusually small number of galaxies. To put that into perspective, a region of that size would normally contain thousands of galaxies, yet the Boötes void appears almost empty in comparison. Its discovery raised questions about how such a vast and underpopulated area could form within a universe shaped by gravity, which tends to pull matter together rather than disperse it. Some theories suggest that voids like this form as matter is drawn toward denser regions, leaving behind expanding empty spaces. Others propose that the Boötes void may be the result of multiple smaller voids merging over time. Despite these ideas, its extreme size and low density remain difficult to fully explain. It stands as a reminder that even on the largest scales, the universe still contains structures that challenge current understanding. And while some regions are defined by what they lack, others are defined by forces so powerful they push the limits of physics itself. Among the most extreme objects in the universe are magnetars, a rare type of neutron star with magnetic fields of unimaginable strength. These fields can reach intensities of around 10 to the power of 11 Tesla, making them trillions of times stronger than the magnetic field of the Earth. The effects of such a field are difficult to comprehend, but even at a distance of half the distance between the Earth and the Moon, a magnetar's magnetic influence would be strong enough to disrupt the atomic structure of matter. In practical terms, it could affect the iron atoms in human blood, altering their alignment and potentially causing severe physical effects. Closer to the magnetar, the environment becomes even more extreme, with magnetic forces capable of distorting atoms and affecting the behavior of light itself. These objects form from the collapsed cores of massive stars, similar to other neutron stars, but with conditions that amplify their magnetic fields to extraordinary levels. Magnetars also produce powerful bursts of high-energy radiation, sometimes releasing more energy in a fraction of a second than the sun emits in years. They represent one of the most intense expressions of physical forces in the universe. And in events where neutron stars interact with one another, those forces can give rise to phenomena that reshape our understanding of how elements are formed. In 2017, scientists observed a groundbreaking event known as GW 170817, marking the first time gravitational waves were detected from the collision of two neutron stars. Gravitational waves are ripples in space-time itself, predicted by Einstein's theory of relativity, and this event provided direct evidence of such a merger. As the two neutron stars spiraled toward each other, they emitted gravitational waves that were detected by instruments on Earth, allowing scientists to track the event in unprecedented detail. At the same time, telescopes observed a burst of light and radiation from the same location, confirming that the collision had occurred. This event was particularly significant because it provided strong evidence for the origin of heavy elements such as gold. During the merger, extreme conditions allowed for rapid nuclear reactions that created these elements and dispersed them into space. This means that materials like gold on Earth may have originated from similar now billions of years ago. The detection of GW 170817 linked gravitational wave astronomy with traditional observations, opening a new way of studying the universe. It showed that even the most violent cosmic events can leave behind elements that eventually become part of planets and life itself. Beyond the already extreme nature of neutron stars, theoretical physics suggests the possible existence of something even more exotic: strange stars. These are hypothetical objects that may form when the pressure inside a collapsing star becomes so intense that protons and neutrons break down into their fundamental components, known as quarks. In this state, matter would no longer exist in the form we are familiar with, but as a dense quark soup, sometimes referred to as strange quark matter. This type of matter could be even denser than that found in neutron stars, packing more mass into an even smaller volume. If strange stars do exist, they would challenge current understanding of how matter behaves under extreme conditions, offering insight into the fundamental structure of the universe. Because they would appear very similar to neutron stars from a distance, identifying them is difficult, and their existence remains unconfirmed. However, scientists continue to search for subtle differences in behavior, such as variations in mass, size, or radiation patterns that could indicate the presence of quark matter. These objects represent a frontier where astrophysics meets particle physics, pushing theories to their limits. And while strange stars explore the smallest building blocks of matter, other cosmic objects demonstrate the opposite extreme, dominating entire galaxies with their immense mass. At the centers of most large galaxies, including our own Milky Way, reside supermassive black holes, objects so massive that they can contain millions or even billions of times the mass of the Sunday. Unlike smaller black holes formed from collapsing stars, these giants are thought to grow over time by absorbing matter and merging with other black holes. Their gravitational influence extends across vast distances, affecting the motion of stars and gas throughout the galaxy. Despite their name, black holes are not empty spaces, but regions where gravity is so strong that nothing, not even light, can escape once it crosses a boundary known as the event horizon. Surrounding many of these black holes are accretion disks, swirling rings of superheated gas that emit intense radiation as material spirals inward. In some cases, they also produce powerful jets that shoot energy and particles far into space. These central black holes play a key role in galaxy formation and evolution, helping to regulate star formation and shape the structure of their host galaxies. Their presence shows how a single object can influence an entire system on a cosmic scale. And while gravity shapes galaxies, chemistry also reveals surprising complexity in the vast regions between stars. In the constellation Aquila, astronomers have identified an enormous cloud of gas containing a surprising ingredient, ethyl alcohol, the same type of alcohol found in beverages on Earth. This cloud is part of a larger region of space rich in complex organic molecules, where conditions allow atoms to combine into more intricate chemical structures. The amount of ethanol present is staggering, estimated to be enough to fill hundreds of trillions of pints of beer. Despite this, the cloud is extremely diffuse, meaning the alcohol is spread out over a vast area, making it far less concentrated than anything we encounter on Earth. The presence of such molecules highlights the complexity of interstellar chemistry, where even in the cold and sparse environment of space, chemical reactions can still occur over long periods. These discoveries suggest that the building blocks of more complex compounds, possibly even those related to life, can form naturally in space. It shows that the universe is not just governed by physics on large scales, but also by intricate chemical processes that take place across immense distances. Orbiting close to the surface of Mars is a small, irregularly shaped moon known as Phobos. Unlike our own moon, which is gradually moving away from Earth, Phobos is slowly spiraling inward toward Mars due to tidal forces between the two bodies. Each orbit brings it slightly closer, and over time, this gradual decay will lead to a dramatic outcome. Scientists estimate that in about 50 million years, Phobos will either crash directly into the surface of Mars, or more likely, be torn apart by the planet's gravity before it can reach it. If it breaks apart, the debris could spread out and form a temporary ring system around Mars, similar in appearance to the rings of Saturn, though much less stable and short-lived. This process highlights how gravitational interactions can shape the evolution of planetary systems over long timescales. Phobos itself is thought to be composed of loosely held material, making it particularly vulnerable to these tidal forces. Its eventual fate is a reminder that even seemingly stable orbits can change over time. And while Phobos represents a future event unfolding slowly, the origin of our own moon traces back to a violent collision in the distant past. The moon that orbits Earth today is widely believed to have formed from a massive collision that occurred about 4.5 billion years ago. According to the leading theory, a Mars-sized body known as Theia struck the early Earth during the chaotic period of planetary formation. The impact was so powerful that it ejected enormous amounts of material from both bodies into space. Over time, this debris began to orbit Earth, gradually coming together under the force of gravity to form the moon. This theory explains several key observations, including the similarities in composition between Earth's outer layers and the moon's surface, as well as the moon's relatively large size compared to its host planet. The collision would have also significantly altered Earth's rotation and tilt, influencing the development of seasons and the stability of the planet's climate. The formation of the moon is therefore not just a story about a satellite, but about an event that helped shape the conditions necessary for life on Earth. It represents a moment of destruction that ultimately led to a stable system. And beyond Earth, other moons in the solar system reveal landscapes shaped by forces just as dramatic. Far from Earth, orbiting the distant planet Uranus, is a moon named Miranda, known for its unusual and extreme surface features. Among its most striking characteristics are enormous cliffs that rise up to 20 kilometers high, making them the tallest known cliffs in the solar system. To put this into perspective, Mount Everest, the highest point on Earth, reaches just under 9 kilometers above sea level. The presence of such massive cliffs suggests a complex geological history. Scientists believe that Miranda may have experienced significant internal activity in the past, possibly caused by tidal forces from Uranus. These forces could have heated the interior, leading to surface deformation and the formation of its unique terrain. Another possibility is that Miranda was once shattered by a massive impact and later reassembled, leaving behind a patchwork surface with sharp contrasts in elevation. The moon's landscape appears fragmented and varied, unlike the smoother surfaces seen on many other moons. Miranda stands as an example of how even small celestial bodies can undergo dramatic changes, resulting in features that rival or exceed those found on much larger worlds. Although the moon appears calm and lifeless from a distance, it is not entirely inactive. Beneath its surface, the moon experiences seismic activity known as moonquakes. These events are similar in concept to earthquakes on Earth, but they behave very differently. While earthquakes usually last only seconds or minutes, moonquakes can continue for much longer, sometimes lasting up to an hour. One reason for this difference lies in the structure of the moon itself. Unlike Earth, which has tectonic plates and a partially molten interior that helps absorb and dissipate energy, the moon is much more rigid and dry. When seismic energy is released, it travels through the moon's interior without being quickly dampened, allowing vibrations to persist for extended periods. Some moonquakes are caused by tidal forces from Earth, which stretch and compress the moon as it orbits, while others may result from temperature changes or meteorite impacts. Despite their long duration, moonquakes are generally weaker than major earthquakes on Earth. However, their extended shaking could pose challenges for future lunar structures or missions. These subtle but persistent movements show that even a seemingly quiet world can still be geologically active. And while the moon reveals hidden activity beneath a stable surface, other moons in the solar system display motion that is far less predictable. Orbiting Saturn is a small, irregularly shaped moon called Hyperion, known for one of the most unusual behaviors observed in the solar system. Unlike most moons, which rotate in a steady and predictable way, Hyperion spins chaotically. This means its rotation is irregular and constantly changing, making it impossible to predict its exact orientation over time. The reason for this lies in a combination of factors, including its uneven shape and the gravitational influence of nearby moons, particularly Titan. Because Hyperion is not spherical, the gravitational forces acting on it vary depending on its position, causing its rotation to shift unpredictably. Instead of having a stable axis like Earth or our moon, Hyperion tumbles through space in a way that appears almost random. This chaotic rotation also affects how sunlight falls on its surface, leading to constantly changing patterns of light and shadow. Its sponge-like appearance, covered in deep craters, adds to its unusual character. Hyperion stands out as a rare example of how complex gravitational interactions can produce motion that defies simple patterns. And while some moons behave unpredictably, others possess features that make them stand out in entirely different ways. Ganymede, the largest moon of Jupiter, is remarkable not only for its size, but also for its unique properties. It is so large that it surpasses the planet Mercury in diameter, making it the biggest moon in the entire solar system. Despite its classification as a moon, Ganymede exhibits characteristics typically associated with planets. One of its most distinctive features is its magnetic field, making it the only known moon to generate one. This magnetic field is believed to originate from a liquid iron or iron sulfide core within its interior, similar to the mechanism that produces Earth's magnetic field. The presence of this field creates a small magnetosphere around Ganymede, interacting with Jupiter's much stronger magnetic environment. Beneath its icy surface, there is also strong evidence of a subsurface ocean, which may contain more water than all of Earth's oceans combined. The surface itself shows a mix of older, heavily cratered regions and younger, grooved terrain, indicating a complex geological history. Ganymede demonstrates that moons can be far more than simple satellites, possessing internal activity and features that rival those of full-sized planets. Far out in the outer solar system, orbiting Saturn, lies one of the most Earth-like worlds in terms of processes, though not in composition. Titan, Saturn's largest moon, has lakes, rivers, and even rainfall. But instead of water, these features are made of liquid methane and ethane. At Titan's extremely low temperatures, these hydrocarbons exist in liquid form, flowing across the surface in a cycle that closely resembles Earth's water cycle. Clouds form in the thick atmosphere, rain falls onto the surface, and liquids collect into vast lakes and seas, particularly near the poles. The landscape includes river channels and shorelines shaped by this continuous movement of liquid. Titan's atmosphere is dense and rich in nitrogen, with complex organic chemistry occurring within it. This makes it one of the most intriguing places in the solar system for studying prebiotic conditions, offering clues about how chemical processes might evolve in different environments. Despite its similarities to Earth in terms of weather and surface activity, Titan remains a cold and alien world where familiar processes take place using entirely different materials. It shows that Earth-like systems are not unique, but can emerge under very different conditions. And while Titan's surface is shaped by flowing liquids, closer to home, another slow but steady process is quietly reshaping the relationship between Earth and its own moon. The moon, which has orbited Earth for billions of years, is not fixed in place, but is gradually moving away. Measurements show that it is drifting outward at a rate of about 3.8 centimeters per year. This slow movement is caused by tidal interactions between the Earth and the moon. As the moon's gravity pulls on Earth's oceans, it creates tides, and the energy from these interactions is transferred in a way that pushes the moon slightly farther away over time. Although the change is small on a yearly basis, over millions of years it becomes significant. In the distant past, the moon was much closer to Earth, appearing larger in the sky and exerting stronger tidal forces. As it continues to move away, the length of Earth's day is also gradually increasing, since the planet's rotation is slowing down slightly as part of this energy exchange. This ongoing process shows how gravitational relationships between celestial bodies are not static but evolve continuously over time. The Earth-Moon system is slowly changing, even if those changes are imperceptible in a human lifetime. And while our moon moves steadily outward, other moons in the solar system follow paths that are far less conventional. Triton, the largest moon of Neptune, stands out because of the direction in which it orbits. Unlike most moons, which orbit in the same direction as their planet's rotation, Triton moves in the opposite direction, a pattern known as a retrograde orbit. This unusual motion strongly suggests that Triton did not form around Neptune, but was instead captured by the planet's gravity long ago. Scientists believe it may have originated in the Kuiper Belt, a distant region of icy objects beyond Neptune, before being pulled into orbit. The capture of Triton would have been a dramatic event, likely disrupting any existing moons Neptune may have had at the time. Triton itself is a cold and geologically active world, with a surface covered in ice and features such as cryovolcanoes that erupt with substances like nitrogen instead of molten rock. Its retrograde orbit and active surface make it one of the most fascinating moons in the solar system. Triton provides a glimpse into how objects can migrate and be reshaped by gravitational forces, showing that not all moons follow the same origin or evolutionary path. On April 12, 1961, Yuri Gagarin made history as the first human to travel into space aboard the spacecraft Vostok 1. The flight lasted just under 2 hours, during which he completed a single orbit around the Earth. Official reports at the time presented the mission as a complete success from launch to landing. However, one detail was kept secret for years. During re-entry, Gagarin did not land inside the capsule as initially claimed. Instead, he ejected from the spacecraft at an altitude of several kilometers and descended separately using a parachute while the capsule landed on its own. This detail was hidden because international aviation rules at the time required a pilot to land with their craft to qualify for official records. By keeping this information confidential, the Soviet Union ensured that Gagarin's achievement would be fully recognized. It was only later, after the rules had changed and the mission was firmly established in history, that the truth became widely known. Despite this hidden detail, the significance of the flight remains unchanged, marking the beginning of human space exploration. And as early missions like Vostok 1 opened the door to space, later missions would go much farther than anyone at the time could have imagined. Today, the most distant human-made object ever created is Voyager 1, launched by NASA in 1977. Originally designed to study the outer planets, Voyager 1 completed its primary mission decades ago, but continued traveling outward into deep space. It has now moved beyond the heliosphere, the region dominated by the Sun's influence, and entered interstellar space. At a distance of over 23 billion kilometers from Earth, signals from the spacecraft take more than 20 hours to reach us. Despite its age, Voyager 1 is still transmitting data, providing valuable information about the environment between stars. Its instruments continue to measure cosmic radiation, magnetic fields, and plasma conditions in a region that had never been explored before. The spacecraft carries a golden record, a message intended for any potential intelligent life that might encounter it in the distant future. Voyager 1 represents humanity's farthest reach into the cosmos, a silent traveler moving through space long after its creators are gone. And while it explores the vast emptiness between stars, Within our own solar system, there are worlds that remain intensely active and dynamic. One of the most geologically active bodies in the entire solar system is Io, a moon orbiting the massive planet Jupiter. Unlike Earth, where volcanic activity is driven by internal heat and plate tectonics, Io's activity is powered by gravitational forces. As it orbits Jupiter, it is constantly pulled and stretched by the planet's immense gravity, as well as by the influence of neighboring moons. This process, known as tidal heating, generates intense internal friction, producing enough heat to fuel widespread volcanic activity. Io is home to more than 400 active volcanoes, some of which erupt with such force that material is ejected hundreds of kilometers above the surface. The landscape is constantly being reshaped, with lava flows and sulfur deposits creating a colorful and ever-changing terrain. Unlike many other moons, Io has very few impact craters, because its surface is continually renewed by volcanic processes. It stands as an extreme example of how gravitational interactions can drive powerful geological activity, making it one of the most dynamic worlds known. Life aboard the International Space Station depends on systems designed to recycle and reuse nearly every available resource. One of the most critical of these is the station's water recovery system, which is capable of turning waste into usable water with remarkable efficiency. In an environment where resupply missions are limited and costly, carrying large amounts of fresh water is not practical. Instead, the station collects moisture from multiple sources, including humidity in the air, sweat, and even urine. Through a series of filtration and purification processes, this water is treated until it meets strict safety standards for drinking. The system is so effective that about 90% of wastewater can be converted back into clean, drinkable water. While the idea may seem unusual at first, the process ensures sustainability and reduces the need for constant resupply from Earth. The recycled water is tested regularly to maintain quality, and astronauts rely on it daily for drinking, food preparation, and hygiene. This closed-loop system demonstrates how living in space requires efficient use of every resource, turning what would be waste on Earth into something essential. And while systems like this support life in orbit, the conditions of microgravity also affect the human body in unexpected ways. In the microgravity environment of space, everyday bodily functions can behave quite differently from how they do on Earth. One surprising example is the simple act of burping. On Earth, gravity helps separate liquids and gases in the stomach, allowing gas to rise and be released as a burp. In space, however, the absence of gravity means that this separation does not occur. Gas and liquid remain mixed together, making it difficult for astronauts to release gas in the usual way. When they do attempt to burp, it can result in what is sometimes referred to as a wet burp, where small amounts of liquid may accompany the gas. Because of this, astronauts are often cautious about their diet, avoiding carbonated beverages that could increase gas buildup. The way the body handles digestion, fluids, and internal pressure is altered in microgravity, requiring astronauts to adapt to these changes over time. This is just one of many examples of how living in space affects normal biological processes. Even simple actions that are taken for granted on Earth can become unfamiliar in orbit. And while daily life aboard a space station presents these challenges, the earliest missions beyond Earth involved adapting to entirely new experiences for the first time. Aboard the International Space Station, astronauts experience a cycle of day and night unlike anything on Earth. The station orbits the planet at a speed of roughly 28,000 kilometers per hour, completing a full orbit approximately every 90 minutes. As a result, those on board witness about 16 sunrises and 16 sunsets within a single Earth day. Each transition from darkness to light happens rapidly, with the sun appearing to rise and set in a matter of minutes. This constant shift creates a unique environment where the usual concept of a day becomes less meaningful. To maintain a stable routine, astronauts rely on coordinated time schedules rather than natural light cycles, often following a standard Earth-based time zone. The frequent changes in light can also affect the body's internal clock, requiring adjustments to sleep patterns and daily activities. Despite these challenges, the view of Earth from orbit, combined with the repeated transitions of light and shadow, provides a striking reminder of the planet's rotation and the station's motion through space. It is an experience that highlights how different life becomes once you leave the surface of the Earth. And while the visual experience of orbit is extraordinary, Returning from spacewalks reveals another unexpected aspect of the space environment. After completing a spacewalk and returning inside the station, astronauts often notice a distinct and unusual smell lingering on their suits. This scent has been described as resembling hot metal, welding fumes, or even gunpowder. The cause of this phenomenon is linked to atomic oxygen, a highly reactive form of oxygen found in the upper layers of Earth's atmosphere where the station orbits. During a spacewalk, this atomic oxygen interacts with the materials on the surface of the spacesuit. When astronauts re-enter the station and remove their equipment, the particles that have bonded to the suit react with the oxygen-rich air inside, producing the noticeable odor. It is not a smell encountered in everyday life on Earth, but rather a result of the unique chemical environment in low Earth orbit. This effect offers a glimpse into how different the conditions of space are compared to the surface of the planet. Even something as simple as a smell becomes a reminder of the extreme and unfamiliar surroundings beyond Earth's atmosphere. And while these external effects are surprising, the absence of gravity also changes how basic physical processes behave within the human body. In the microgravity environment of space, even something as simple as crying behaves very differently. On Earth, tears fall downward due to gravity, quickly moving away from the eyes. In space, however, there is no force pulling them down, so tears do not fall at all. Instead, they accumulate and form a floating, wobbling sphere of liquid around the eye. Surface tension causes the liquid to cling together, creating a bubble-like shape that can grow as more tears are produced. This can lead to discomfort, as the liquid may remain in contact with the eye and surrounding skin rather than being cleared away. Astronauts must sometimes wipe the tears away manually to relieve the irritation. The way fluids behave in microgravity affects not only tears, but also other bodily functions, including how blood circulates and how moisture distributes across surfaces. These small but noticeable differences highlight how gravity influences everyday experiences in ways that are often taken for granted. Surrounding Earth is an invisible but increasingly crowded region filled with human-made objects traveling at extraordinary speeds. This collection of material, often referred to as space debris, includes everything from defunct satellites and discarded rocket stages to fragments created by past collisions and explosions. More than 27,000 of these objects are actively tracked, and countless smaller pieces remain too tiny to monitor but still potentially dangerous. What makes this debris especially hazardous is its velocity. Traveling at speeds of up to 28,000 kilometers per hour, even a small fragment can carry enough energy to damage or destroy a spacecraft upon impact. This creates a growing challenge for space operations, as satellites and missions must constantly navigate through this environment to avoid collisions. As more launches take place, the amount of debris continues to increase, raising concerns about the long-term sustainability of activities in orbit. Scientists and engineers are now working on methods to reduce and manage this debris, including designing satellites that can safely deorbit at the end of their missions. It is a reminder that human activity has extended beyond Earth in ways that require careful management, and while space can appear vast and empty, even small objects can leave a lasting presence in orbit. During the Apollo 14 mission in 1971, astronaut Alan Shepard carried out one of the most unusual moments in space exploration. While on the lunar surface, Shepard attached a makeshift golf club head to a tool handle and proceeded to hit 2 golf balls across the moon's dusty terrain. Because of the moon's lower gravity, about 1/6 that of Earth, the balls traveled much farther than they would have under normal conditions. Shepard famously remarked that one of the shots went miles and miles, though later estimates suggest the distances were somewhat shorter. Despite this, the moment became iconic, blending human curiosity and humor with a historic mission. The golf balls remain on the moon to this day, untouched and preserved in the airless environment where there is no wind or weather to move them. This small act highlights how even in the midst of serious scientific exploration, moments of creativity and spontaneity can occur. It also shows how objects left on the moon can remain unchanged for extremely long periods of time. And beyond these symbolic items, astronauts also left behind tools that continue to serve a scientific purpose decades later. Among the most important instruments placed on the moon during the Apollo missions are devices known as retroreflectors. These were left by several missions, including Apollo 11 and later expeditions, as part of experiments designed to measure the distance between the Earth and the Moon with high precision. A retroreflector is a special type of mirror that reflects light directly back toward its source, regardless of the angle at which it arrives. Scientists on Earth can fire laser beams at these reflectors, and by measuring the time it takes for the light to return, they can calculate the exact distance to the Moon. This method has been used for decades and continues to provide valuable data about the Moon's orbit and its gradual movement away from Earth. The measurements are precise enough to detect changes of just a few centimeters over time. These instruments represent one of the longest-running experiments in space science, showing how a simple device can continue to contribute to our understanding of the Earth-Moon system long after the missions themselves have ended. Each year, Earth experiences countless impacts from small asteroids and meteoroids, most of which go unnoticed. While many burn up in the atmosphere, some collisions are powerful enough to eject material from the planet's surface into space. Scientists estimate that around 1 billion kilograms of rocky debris are launched away from Earth annually through these impacts. Some of this material can escape Earth's gravitational pull entirely, traveling through space and potentially reaching other bodies such as the Moon or even Mars. This process has led to the idea that life, or at least the building blocks of life, could be transferred between planets in a concept known as panspermia. If microorganisms were embedded within rocks that were ejected into space, it is possible that they could survive the journey under certain conditions and eventually land elsewhere. Evidence supporting this includes meteorites found on Earth that originated from Mars, showing that material exchange between planets does occur. While the likelihood of life surviving such journeys remains an area of ongoing research, the possibility suggests that planets may not be completely isolated systems. Instead, they could be connected through the transfer of material over long periods of time. And while these exchanges happen naturally on a planetary scale, the human body itself undergoes noticeable changes when it leaves Earth behind. When astronauts travel into space and spend extended periods in microgravity, their bodies begin to adapt in ways that can be surprising. One of the most noticeable changes is an increase in height. Without the constant pull of gravity compressing the spine, the vertebrae are able to expand slightly, allowing astronauts to grow taller. On average, this increase can be up to about 5 centimeters during a mission. The effect is temporary, and once astronauts return to Earth, gravity gradually compresses the spine back to its original length. While this might seem like a minor change, it can cause discomfort, especially in the lower back, as the body adjusts to the new conditions. Spacecraft and equipment must also be designed with this change in mind, ensuring that astronauts can still move comfortably within confined spaces. This demonstrates that time is not an absolute, fixed quantity, but something that can vary depending on location and gravitational conditions. It challenges the intuitive idea that time flows uniformly everywhere. Even though the effect is minimal in daily experience, it becomes much more significant in stronger gravitational fields, such as near massive stars or black holes. And when gravity and motion combine, as they do in space travel, the effects on time become even more noticeable. Astronauts aboard the International Space Station experience time slightly differently from people on Earth. This is due to a combination of two effects described by Einstein's theory of relativity: gravitational time dilation and time dilation caused by motion. Because the ISS orbits Earth at very high speeds, around 28,000 kilometers per hour, time for astronauts slows down slightly compared to those on the ground. At the same time, being farther from Earth's center means they experience slightly weaker gravity, which would tend to make time pass faster. However, the effect of their high speed is stronger, resulting in a net slowing of time. Over the course of a year, this difference amounts to about 7/1000ths of a second. While this is an extremely small amount, it has been measured and confirmed through precise experiments. This means that astronauts age just a tiny bit more slowly than people on Earth, making space travel a real-world example of time dilation in action. In many parts of the universe, stars are not alone, but exist in binary systems, where two stars orbit around a common center of mass. In some of these systems, the stars are close enough that one can begin to draw material away from the other. This process is especially dramatic when a dense star, such as a white dwarf, pulls gas from a companion star. Over time, this stolen material accumulates on the surface of the white dwarf, increasing its mass. There is a critical limit, known as the Chandrasekhar limit, beyond which the star can no longer support itself against gravity. When this threshold is reached, the star undergoes a sudden and catastrophic collapse, triggering a powerful explosion known as a Type Ia supernova. These explosions are incredibly bright, often outshining entire galaxies for a short period. Because they occur at a consistent mass threshold, Type Ia supernovae are used by astronomers as standard candles to measure distances across the universe. This process of one star gradually consuming another, only to end in a violent explosion, highlights the dynamic and sometimes destructive interactions that can occur in stellar systems. And while some stars behave in predictable ways, others present mysteries that challenge current scientific understanding. One of the most unusual stars ever discovered is known as Przybylski's star, a celestial object that has puzzled astronomers for decades. What makes this star so strange is the presence of elements in its spectrum that are highly unstable and should decay rapidly, meaning they should not persist naturally over long periods of time. These elements, including certain radioactive materials, are typically short-lived on cosmic timescales, yet they appear to be present in measurable quantities within the star. This raises the question of how they are being produced or maintained. Some scientists have proposed that unknown nuclear processes may be occurring within or near the star, continuously generating these elements. Others suggest that interactions with a companion object or remnants of past events could play a role. Despite ongoing research, no single explanation has fully resolved the mystery. Przybylski's star serves as a reminder that there are still phenomena in the universe that do not fit neatly into established models, pointing to gaps in our understanding of stellar physics. And when considering the scale at which such mysteries exist, the size of the universe itself adds another layer of complexity. The observable universe is estimated to be about 93 billion light-years in diameter, a figure that seems to contradict its age of approximately 13.8 billion years. At first glance, it might appear impossible for light to have traveled such a distance in that time. However, this apparent contradiction is explained by the expansion of space itself. When light began its journey from distant regions of the universe, those regions were much closer together. As the universe expanded over billions of years, the space between objects stretched, increasing the distance that light had to travel. This means that by the time the light reaches us, the objects it originated from are now much farther away than they were when the light was emitted. The expansion of space can effectively increase distances faster than the speed of light, not because objects are moving through space at that speed, but because space itself is growing. This concept allows for a universe that is far larger than its age alone might suggest. Among the oldest known stars in the universe is Methuselah, HD 140283, a faint, ancient object located in our galaxy. This star is estimated to be about 13.7 billion years old, making it nearly as old as the universe itself. Its age was determined by analyzing its composition and luminosity, particularly the low abundance of heavier elements within it. In astronomy, elements heavier than hydrogen and helium are produced in later generations of stars, so a star with very few of these elements is likely to have formed early in cosmic history. Methuselah is considered a population 2 star, meaning it was born when the universe was still young and had not yet been enriched by multiple cycles of stellar evolution. For a time, estimates of its age even appeared to exceed the age of the universe, which led to significant debate and refinement of measurement techniques. While improved data has resolved most of these discrepancies, Methuselah remains a remarkable object that offers insight into the early stages of star formation. It acts as a kind of living fossil, preserving information about conditions that existed shortly after the Big Bang. And while some stars have endured since near the beginning of time, others follow a much longer and quieter path after their active life ends. When stars like our Sun reach the end of their life cycle, they shed their outer layers and leave behind a dense core known as a white dwarf. These stellar remnants no longer produce energy through nuclear fusion and instead slowly cool over time. Initially, white dwarfs are extremely hot, but without an internal energy source, they gradually lose heat, radiating it away into space. This cooling process is incredibly slow, taking trillions of years to complete. In theory, if given enough time, a white dwarf would eventually cool, to the point where it no longer emits significant light or heat, becoming what is known as a black dwarf. However, no black dwarfs are known to exist in the universe today. This is because the universe itself is not old enough for any white dwarf to have cooled to that stage. Even the oldest white dwarfs still retain residual heat from their earlier phases. The concept of black dwarfs represents a glimpse into the far future of the universe, a time when stellar remnants have faded into darkness. It highlights how cosmic processes often unfold on timescales far beyond human comprehension, and while some stars fade slowly over unimaginable periods, others end their lives in a far more dramatic and direct way. Not all stars follow the same path when they reach the end of their lives. For extremely massive stars, the collapse process can bypass the typical supernova explosion altogether. In many cases, when a massive star exhausts its nuclear fuel, its core collapses under gravity and triggers a supernova, leaving behind a neutron star or black hole. However, if the star is sufficiently massive, the collapse can be so intense that it proceeds directly into a black hole without producing a visible explosion. In these cases, the outer layers of the star may fall inward rather than being blasted outward, resulting in what is sometimes referred to as a failed supernova. Observations have provided evidence for this process, as astronomers have detected stars that appear to simply vanish without the bright flash expected from a supernova. This direct collapse shows that stellar death is not always a violent or luminous event, but can sometimes occur quietly, with the star disappearing into a black hole. It reveals yet another variation in how stars evolve and end their lives, shaped by their initial mass and internal conditions. One of the most puzzling stars ever observed is KIC 8462852, often referred to as Tabby's star. Located in the constellation Cygnus, this star has drawn attention because of its unusual and unpredictable dimming patterns. Most stars that vary in brightness do so in regular, repeatable ways, often due to orbiting planets or natural pulsations. However, Tabby's star behaves differently. Its light can drop suddenly and irregularly, sometimes by significant amounts, without a consistent pattern. Early speculation even suggested the possibility of large artificial structures blocking the star's light, though this idea remains highly unlikely. More plausible explanations include clouds of dust, fragments of comets, or debris from collisions within the system. Despite years of observation and analysis, no single explanation has fully accounted for all of its behavior. The mystery of Tabby's star highlights how even well-studied objects like stars can still surprise scientists, revealing gaps in our understanding of stellar environments. It stands as a reminder that the universe continues to present phenomena that do not fit neatly into existing models. And while some stars challenge our understanding through unusual behavior, others impress simply through their immense size. One of the most famous giant stars is Betelgeuse, a red supergiant located in the constellation Orion. This star is enormous compared to our Sun, with a radius so large that if it were placed at the center of our solar system, its outer layers would extend beyond the orbit of Jupiter. To imagine this, consider that the distance from the Sun to Jupiter is already vast, spanning hundreds of millions of kilometers. Yet Betelgeuse would fill that entire space. Despite its size, Betelgeuse is relatively cool compared to smaller stars, giving it a reddish appearance. It is also nearing the end of its life, and is expected to explode as a supernova at some point in the future, though exactly when remains uncertain. Observations of Betelgeuse have revealed fluctuations in brightness, some of which have sparked interest in whether it is approaching that final stage. Its sheer scale provides a sense of how diverse stars can be, ranging from small, dense remnants to massive giants that dominate their surroundings. And when we consider the number of such stars that exist, the scale becomes even more difficult to comprehend. The observable universe contains an estimated number of stars so large that it exceeds even the vast quantities we encounter on Earth. Astronomers often compare this number to grains of sand, suggesting that there are more stars in the universe than grains of sand on all of Earth's beaches combined. While it is difficult to assign an exact figure, estimates suggest there may be hundreds of billions of galaxies, each containing billions or even trillions of stars. This comparison helps convey the immense scale of the cosmos in a way that is easier to visualize. Each of these stars may host its own system of planets, increasing the potential for diverse environments across the universe. The sheer number of stars emphasizes how small our solar system is in comparison. It also highlights the vast number of opportunities for different kinds of stellar systems to exist. And among these countless stars, some exhibit behavior that is both extreme and precise. Among the most remarkable stellar remnants are neutron stars, incredibly dense objects formed from the collapsed cores of massive stars. Some neutron stars rotate at extraordinary speeds, with certain examples spinning up to 716 times per second. As they spin, they emit beams of electromagnetic radiation, particularly in the radio spectrum, from their magnetic poles. If these beams sweep past Earth, they are detected as regular pulses, giving rise to the name pulsars. This behavior is often compared to a lighthouse, where the rotating beam appears as a flashing signal to a distant observer. The precision of these pulses can be astonishing, with some pulsars maintaining incredibly stable timing over long periods. Despite their small size, typically only about 20 kilometers across, neutron stars contain more mass than the Sun, resulting in extremely strong gravity. Their rapid rotation and intense magnetic fields create some of the most extreme conditions known in the universe. Deep within Neptune, far beneath its thick atmosphere of hydrogen, helium, and methane, conditions become so extreme that matter behaves in ways unlike anything on Earth. The pressure and temperature inside the planet's interior are immense, reaching levels capable of transforming common elements into entirely different states. One of the most fascinating predictions is that carbon atoms, subjected to these conditions, are compressed so intensely that they form diamond structures. Some models suggest that this process could create what is often described as a diamond rain, where carbon crystallizes and falls deeper into the planet. In even more extreme layers, it has been proposed that carbon could exist in a fluid state, forming a kind of liquid diamond ocean. While this concept is based on theoretical models and laboratory experiments simulating high-pressure environments, it reflects how unusual planetary interiors can be. Neptune, along with Uranus, belongs to a class of planets known as ice giants, where water, ammonia, and methane exist under pressures that turn them into exotic, superheated fluids. These extreme environments challenge our understanding of matter and chemistry, showing that the behavior of elements can change dramatically under different conditions. And while distant planets reveal strange possibilities, our own planet holds its own unique distinction. Among all the planets in our solar system, Earth stands out as the densest. Density refers to how much mass is packed into a given volume, and despite not being the largest planet, Earth has the highest average density of them all. This is largely due to its composition, particularly its large iron and nickel core. The core accounts for a significant portion of Earth's mass and contributes to its overall density. In contrast, gas giants like Jupiter and Saturn are composed mostly of lighter elements such as hydrogen and helium, which lowers their average density despite their enormous size. Even the other rocky planets, like Mars and Mercury, do not match Earth's density, as their internal structures and compositions differ. Earth's density also plays a role in its gravity, which is strong enough to retain an atmosphere and support liquid water on its surface, both of which are essential for life as we know it. This balance of size, composition, and gravity makes Earth uniquely suited for sustaining complex ecosystems. And while Earth's internal structure defines its physical properties, the star it orbits undergoes processes that shape the entire solar system. At the center of our solar system, the Sun is constantly undergoing nuclear fusion, a process that converts mass into energy. In its core, hydrogen atoms are fused together to form helium, releasing enormous amounts of energy in the process. This energy is what powers the sunlight that reaches Earth and supports life. However, this process comes with a cost. The Sun is gradually losing mass. Every second, approximately 4 million tons of mass are converted into energy, according to Einstein's equation E equals mc squared. While this number is enormous on human scales, it represents only a tiny fraction of the Sun's total mass, meaning the Sun can continue shining for billions of years. Over time, though, this steady loss of mass will contribute to changes in the Sun's structure and behavior as it evolves. Eventually, the Sun will exhaust its hydrogen fuel and enter later stages of its life cycle. For now, This ongoing conversion of mass into energy remains the fundamental process that sustains the solar system. Far beyond Neptune, in the cold outer reaches of the solar system, Pluto and its largest moon, Charon, form one of the most unusual planetary relationships known. Unlike most planet-moon systems, where the moon is clearly smaller and orbits a dominant planet, Pluto and Charon are so similar in relative size that they are often described as a binary system. What makes their interaction especially unique is that they are tidally locked to each other. This means that Pluto always shows the same face to Charon, and Charon always shows the same face to Pluto. As they orbit their shared center of mass, neither body rises or sets in the other's sky, they remain fixed in place. This creates a completely different kind of celestial experience compared to what we see on Earth with our moon. The gravitational forces between them have synchronized their rotations over time, locking them into this permanent orientation. Their shared gravitational balance point even lies outside Pluto's surface, which is rare for a planet-moon pair. This unusual relationship provides insight into how gravity can shape the motion and behavior of celestial bodies over long periods. And while Pluto and Charon show a delicate balance between two worlds, other planets in the solar system present environments far more extreme and unfamiliar. Jupiter, the largest planet in the solar system, is fundamentally different from rocky planets like Earth. It is a gas giant, composed mostly of hydrogen and helium, with no clearly defined solid surface. If you were somehow able to descend into Jupiter, you would not encounter a surface to stand on. Instead, you would pass through layers of thick clouds, entering regions where the gas becomes denser and more compressed the deeper you go. As pressure increases, the hydrogen begins to behave like a liquid, and even deeper still, it transitions into a form known as metallic hydrogen, where it conducts electricity like a metal. The conditions within Jupiter are so extreme that the distinction between gas and liquid becomes blurred, creating a continuous gradient rather than distinct layers. The pressure and temperature would increase rapidly, making survival impossible long before reaching the deeper regions. Despite the lack of a solid surface, Jupiter has a complex internal structure and a powerful magnetic field generated by the movement of its internal materials. This planet demonstrates how diverse planetary environments can be, ranging from solid, rocky worlds to vast, fluid giants. And closer to Earth, even small celestial bodies can behave in surprising ways. Mars, often called the Red Planet, has two small moons known as Phobos and Deimos. Of the two, Phobos is particularly intriguing due to its extremely low gravity. Because it is so small and has so little mass, the gravitational pull on its surface is only about 1/1000th of what we experience on Earth. This means that movement on Phobos would feel completely different. A simple jump could send you soaring high above the surface, and with enough force, you could potentially throw an object fast enough for it to enter orbit around the moon. This low gravity also affects how the surface evolves, with loose material not settling in the same way it would on a larger body. Phobos orbits very close to Mars and is gradually moving closer over time, meaning it may eventually break apart due to tidal forces or collide with the planet. Its small size and weak gravity make it a fascinating example of how different conditions can be on celestial bodies within our own solar system. Saturn's rings are among the most visually striking features in the solar system, stretching across a visual distance of about 282,000 kilometers from edge to edge. At that scale, they appear vast and solid, almost like a continuous disk encircling the planet. But in reality, they are astonishingly thin. On average, Saturn's rings are only about 10 to 30 meters thick, roughly the height of a small building. This creates a structure that is incredibly wide, yet extremely flat, more like a cosmic sheet than a solid ring. The rings are made up of countless particles, ranging in size from tiny grains of ice to chunks as large as houses. These particles orbit Saturn in a delicate balance, guided by gravity and shaped by interactions with the planet's many moons. Some of these moons act as shepherds, keeping the ring material confined and creating gaps and patterns within the rings. Despite their massive appearance, if you could pass through them, you would find mostly empty space between the particles. This contrast between their enormous width and paper-thin structure makes Saturn's rings one of the most unusual formations in the solar system, showing how scale and space can be deceptive. And while Saturn's rings reveal surprising physical properties, the planet itself holds an equally unexpected characteristic. Saturn is unique among the planets in our solar system because it is less dense than water. Density measures how much mass is packed into a given volume, and in Saturn's case, its composition plays a major role. The planet is made primarily of hydrogen and helium, the lightest elements in the universe. Even though Saturn is enormous, large enough to fit more than 700 Earths inside it, its average density is so low that, in theory, it could float if there were an ocean large enough to hold it. Of course, such an ocean does not exist, but the comparison helps illustrate just how light Saturn is for its size. This low density is also related to its internal structure, where layers of gas transition into liquid under increasing pressure. The planet's rapid rotation causes it to bulge at the equator, giving it a noticeably flattened shape. Saturn's composition and structure highlight how different gas giants are from rocky planets like Earth, not just in size, but in fundamental physical properties. And while Saturn challenges expectations with its lightness, the innermost planet of the solar system presents an entirely different kind of surprise. Mercury, the closest planet to the Sun, is known for its extreme temperatures, with surface conditions that can swing from intensely hot during the day to freezing cold at night. Given its proximity to the Sun, it might seem impossible for ice to exist anywhere on the planet. However, scientists have discovered that Mercury does indeed contain water ice, hidden within permanently shadowed craters near its poles. These craters are located in regions where sunlight never reaches, due to Mercury's very small axial tilt. As a result, temperatures inside these shadowed areas remain extremely low, cold enough to trap and preserve ice over long periods of time. Radar observations and spacecraft missions have confirmed the presence of these icy deposits, suggesting that water has been delivered to Mercury by comets or asteroids and then trapped in these cold regions. This discovery reveals how even the harshest environments can contain unexpected pockets of stability. It also demonstrates how local conditions, such as shadow and temperature, can create microenvironments that differ dramatically from the surrounding landscape. Uranus is one of the most unusual planets in the solar system, not because of its size or composition, but because of the way it rotates. Unlike most planets, which spin upright with only slight tilts, Uranus is tipped over dramatically at an angle of about 98 degrees. This means it essentially rotates on its side, as if it were rolling around the Sun rather than spinning like a top. Scientists believe this extreme tilt was likely caused by a massive collision early in the planet's history, possibly with an object the size of Earth. This orientation creates highly unusual seasons. For long periods, one pole faces the Sun continuously while the other remains in darkness, leading to decades-long summers and winters. As Uranus orbits the Sun over 84 Earth years, these conditions slowly reverse. Its rings and moons also follow this tilted alignment, orbiting around the planet's sideways axis. This unique rotation makes Uranus stand out among the planets and shows how violent events in the early solar system could shape planetary behavior in lasting ways. And while Uranus presents a strange kind of balance, another distant planet is known for something far more extreme in motion. Neptune, the outermost major planet in the solar system, is home to the fastest winds ever recorded on any planet. Despite being far from the Sun and receiving very little solar energy, Neptune's atmosphere is incredibly dynamic. Winds on the planet can reach speeds of up to 2,100 kilometers per hour, far exceeding those found on Earth or any other planet. These winds drive massive storms and cloud formations, creating a constantly shifting atmosphere. One of the most famous features observed on Neptune was the Great Dark Spot, a storm system similar in some ways to Jupiter's Great Red Spot, though it appeared and disappeared over time. The source of Neptune's intense winds is still not fully understood, especially given its low external energy input from the sunday. Scientists believe internal heat may play a significant role, as Neptune radiates more energy than it receives. The combination of internal heat and atmospheric dynamics creates conditions that allow for such extreme wind speeds. This makes Neptune a fascinating example of how planetary atmospheres can behave in unexpected ways. And while Neptune's winds dominate its skies, closer to home, Mars holds a structure so vast that it challenges how we perceive size itself. On the surface of Mars lies Olympus Mons, the largest volcano in the entire solar system. This enormous structure rises about 22 kilometers above the surrounding plains, making it nearly 3 times taller than Mount Everest. However, what makes Olympus Mons truly extraordinary is not just its height, but its immense width. The volcano spans hundreds of kilometers across, so large that if you stood at its center, you would not be able to see its edges due to the curvature of Mars itself. The gentle slopes of the volcano extend so far that the horizon would obscure its full scale. Olympus Mons formed over long periods of volcanic activity, with lava flows building up layer upon layer. Mars's lower gravity allowed these flows to spread out more easily, contributing to the volcano's massive size. Additionally, because Mars does not have active plate tectonics like Earth, the volcanic hotspot that created Olympus Mons remained in the same place, allowing the structure to grow continuously over time. Venus is one of the most unusual planets in the solar system, and one of its strangest features is the way it rotates. Unlike most planets, which spin in the same direction as they orbit the Sun, Venus rotates in the opposite direction. This is known as retrograde rotation. As a result, if you were standing on the surface of Venus, you would see the Sun rise in the west and set in the east, the reverse of what we experience on Earth. The reasons for this backward rotation are still not fully understood, but scientists believe it may have been caused by massive collisions early in the planet's history or by long-term atmospheric interactions that gradually altered its spin. Venus also rotates extremely slowly, taking about 243 Earth days to complete a single rotation. This slow, backward spin contributes to the planet's extreme environment, where temperatures remain consistently high across its surface. Thick clouds trap heat in a runaway greenhouse effect, making Venus the hottest planet in the solar system. Its unusual rotation highlights how planets can evolve in very different ways depending on their history and conditions. And when we look at other planets, we find even more surprising relationships between rotation and time. Mercury, the closest planet to the Sun, presents a fascinating example of how orbital motion and rotation can interact in unexpected ways. On Mercury, a single day defined as the time it takes for the Sun to return to the same position in the sky is longer than an entire year. Mercury completes one orbit around the Sun in just 88 Earth days, but it rotates very slowly on its axis, taking about 59 Earth days to complete one full rotation. However, because of the way its rotation and orbit are synchronized in what is called a 3-to-2 resonance, the time from one sunrise to the next on Mercury is about 176 Earth days. This means that if you were standing on Mercury, you would experience a day that lasts twice as long as its year. During this long day, temperatures can swing dramatically, from extremely hot when facing the Sun to extremely cold when in darkness. This unusual relationship between rotation and orbit makes Mercury one of the most unique planets in terms of how time is experienced on its surface. And while Mercury challenges our understanding of time, another planet showcases the persistence of powerful natural forces. Jupiter, the largest planet in the solar system, is home to one of the most enduring storms ever observed, the Great Red Spot. This Vishal storm has been raging for at least 350 years, and possibly much longer, making it one of the longest-lasting atmospheric phenomena known. The Great Red Spot is a Vishal anticyclonic storm, meaning it rotates in a direction opposite to the planet's overall atmospheric flow. It is so large that it could easily engulf Earth, though it has been gradually shrinking over time. The storm's reddish color is thought to come from chemical reactions in Jupiter's upper atmosphere, possibly involving compounds brought up from deeper layers. Despite its age, the Great Red Spot remains active, driven by the complex dynamics of Jupiter's atmosphere, which includes strong jet streams and turbulent weather systems. Unlike storms on Earth, which are powered by heat from the surface and dissipate relatively quickly, Jupiter's storms are sustained by internal heat and the planet's rapid rotation. A black hole is often imagined as something unimaginably large, but its size depends entirely on its mass. If you were to compress the Sun into a black hole, it would shrink down to an object only about 6 kilometers across. This boundary is known as the event horizon, the point beyond which nothing, not even light, can escape. The reason such an enormous mass can fit into such a small region lies in the nature of gravity. When a massive star collapses under its own gravity, there is nothing left to counterbalance that force, and the matter is compressed to an extreme density. In the case of a solar mass black hole, all of the sun's mass would be packed into a sphere roughly the size of a small city. Despite this small size, its gravitational pull would remain just as strong as the sun's at a distance, meaning the planets would continue orbiting it in the same way if the transformation happened without other effects. This shows that black holes are not necessarily giant cosmic voids, but rather incredibly dense points where mass is concentrated into a tiny volume. And while gravity can compress matter to astonishing extremes, there are also fundamental rules in physics that resist this collapse. One of the key principles that prevents matter from collapsing indefinitely under gravity is the Pauli exclusion principle, a rule from quantum mechanics. This principle states that no two electrons can occupy the same quantum state at the same time. In simple terms, it means that particles resist being squeezed into the same space in identical ways. This resistance creates a form of pressure, known as degeneracy pressure, which plays a crucial role in supporting certain types of stellar remnants. In white dwarfs, electron degeneracy pressure prevents further collapse. In even denser objects like neutron stars, a similar effect involving neutrons helps hold the star up against gravity. Without this principle, matter could be compressed indefinitely, and structures like atoms, stars, and even solid objects would not exist as we know them. The Pauli exclusion principle is therefore fundamental to the stability of matter throughout the universe. It acts as a kind of invisible barrier, preventing total collapse under gravitational forces. And while these quantum effects govern the behavior of matter at the smallest scales, planetary motion can also produce surprising and counterintuitive results. Venus once again stands out among the planets due to its extremely slow rotation. A single rotation on its axis takes about 243 Earth days, while it completes an orbit around the Sun in about 225 Earth days. This means that one full day on Venus, from one sunrise to the next, is actually longer than an entire Venusian year. Combined with its retrograde rotation, this creates a very unusual cycle of day and night. If you were on the surface, the sun would move slowly across the sky in the opposite direction compared to Earth, taking an incredibly long time to rise and set. This slow rotation also contributes to the planet's extreme atmospheric conditions. Thick clouds trap heat efficiently, and because the planet rotates so slowly, temperatures remain relatively consistent across its surface, with little variation between day and night. Venus demonstrates how differences in rotation and orbital dynamics can create environments that are vastly different from what we experience on Earth. In the vacuum of space, materials can behave in ways that seem almost impossible by everyday standards. One striking example is a phenomenon known as cold welding. When two pieces of the same metal come into contact in space, they can bond together permanently without the need for heat or melting. On Earth, this does not normally happen because surfaces are covered in microscopic layers of air, moisture, and contaminants that prevent direct contact between atoms. In space, however, the absence of an atmosphere means these protective layers are not present. If two clean, flat metal surfaces touch, their atoms can align and share electrons, effectively merging into a single piece of material. This process can create bonds as strong as if the metal had been welded using traditional methods. Cold welding has important implications for spacecraft design, as moving metal parts can unintentionally stick together, causing mechanical failures. Engineers must carefully design components to avoid this effect, often by using coatings or different materials. This phenomenon shows how removing something as simple as air can completely change the way matter behaves. And while space alters physical interactions at the atomic level, it also transforms something far more abstract, our experience of time itself. Near a black hole, the passage of time behaves in a way that defies everyday intuition. According to Einstein's theory of general relativity, strong gravitational fields can slow down time, a phenomenon known as gravitational time dilation. The closer an object gets to a black hole, the stronger the gravitational pull it experiences, and the more time slows down relative to an outside observer. If you were to watch a clock approaching a black hole from a safe distance, you would see it tick more and more slowly as it neared the event horizon. From the perspective of the object itself, however, time would seem to pass normally. This difference in perception highlights how time is not absolute, but depends on the observer's position in a gravitational field. In extreme cases, such as near a supermassive black hole, the effect can become significant enough to measure directly. This means that two observers in different gravitational environments could age at different rates. The warping of time near black holes is one of the most profound consequences of relativity, showing that gravity does not just influence motion, but the very flow of time itself. And when we consider how physics behaves under such extreme conditions, even abstract concepts like possibility take on new meaning. The number of possible chess games is often used to illustrate the vastness of combinatorial possibilities. Even though chess is played on a finite board with a fixed set of rules, the number of potential game sequences is astronomically large, far exceeding the number of atoms in the observable universe. This number, sometimes referred to as the Shannon number, demonstrates how quickly possibilities can grow when multiple choices are available at each step. However, in the realm of physics, even this enormous number is overshadowed by the number of possible quantum states that can exist near a black hole. Black holes are thought to encode information on their surface area, and the number of ways particles can be arranged within or around them leads to an almost unimaginably large number of possible states. This comparison highlights the difference between human-scale complexity and the deeper complexity found in the laws of nature. While chess represents a system of rules and decisions, quantum physics describes a reality where possibilities exist on a scale that challenges comprehension. When we look up at the sun, the light we see feels immediate, but in reality, it has already been traveling for about 8 minutes before reaching Earth. What's even more surprising is that this final journey is only a tiny fraction of the light's total travel time. The energy that becomes sunlight is created deep within the sun's core through nuclear fusion, where hydrogen atoms combine to form helium. From that moment, the energy begins a long and chaotic journey outward. Inside the sun, photons do not travel in straight lines. Instead, they are constantly absorbed and re-emitted by particles in a dense, turbulent environment. This process, often described as a random walk, can take tens of thousands to hundreds of thousands of years before the energy finally reaches the surface. Only then does it escape into space, traveling quickly and directly to Earth in just minutes. This means that the sunlight warming your skin today began its journey long before human civilization existed. It is a reminder that even something as familiar as sunlight carries a deep and hidden history. And when we shift our focus from stars to the structure of matter itself, we find equally surprising insights. At the atomic level, matter is mostly empty space. Atoms consist of a tiny, dense nucleus surrounded by electrons that occupy regions far larger than the nucleus itself. If all this empty space were removed, the remaining matter would be incredibly compact. In fact, if you could compress every atom in every human on Earth by eliminating this empty space, the entire global population could fit into a volume roughly the size of a sugar cube. This idea is difficult to visualize because the emptiness within atoms is not something we experience directly. The solidity we feel in everyday objects comes not from tightly packed matter, but from electromagnetic forces that prevent atoms from passing through one another. This hidden structure reveals that what appears solid is mostly space, held together by fundamental forces. It also highlights how different scales of reality can produce dramatically different perceptions. While our world feels dense and continuous, at a deeper level it is sparse and structured. And just as atoms contain hidden emptiness, the universe itself carries traces of its earliest moments. Throughout all of space, there exists a faint glow known as the cosmic microwave background radiation. These are photons that originated shortly after the Big Bang, when the universe was still hot and dense. As the universe expanded, these photons stretched and cooled, shifting from visible and infrared light into the microwave part of the spectrum. Today, they fill the entire universe almost uniformly, providing a snapshot of what the cosmos looked like about 380,000 years after its beginning. This radiation is one of the strongest pieces of evidence for the Big Bang, as it represents the leftover heat from that early phase. Sensitive instruments can detect tiny variations in this background, revealing information about the structure and evolution of the universe. These ancient photons have been traveling for billions of years, carrying with them a record of the universe's earliest conditions. Neutron stars are among the most extreme objects in the universe, formed when massive stars collapse under their own gravity after a supernova. What remains is a core so dense that protons and electrons are forced together to form neutrons, creating matter unlike anything found on Earth. The result is an object with an extraordinary density. To put this into perspective, a single teaspoon of neutron star material would weigh about 10 million tons if brought to Earth. This means that a tiny amount of this matter would outweigh entire mountains. The reason for this extreme density lies in the collapse of the star's core, where gravity compresses matter beyond normal atomic structure. Electrons are pushed into protons, eliminating the empty space that usually exists within atoms. What remains is tightly packed nuclear matter, held together by immense gravitational forces and supported by quantum effects such as neutron degeneracy pressure. Despite being only about 20 kilometers across, neutron stars can contain more mass than the Sun. Their gravity is so strong that it significantly bends light and time around them. This level of density is almost impossible to imagine in everyday terms, yet it exists naturally in the universe. And while neutron stars represent matter compressed to its limits, the space between objects tells a very different story. Although space is often described as a vacuum, it is not completely empty. On average, there are still a few particles present in even the most remote regions of the universe. Typically, this amounts to about 5 hydrogen atoms per cubic meter. Compared to the density of air on Earth, which contains trillions of molecules in the same volume, this is incredibly sparse. However, it is not zero. These particles are remnants of cosmic processes, including the formation of stars and the expansion of the universe following the Big Bang. In some regions, such as interstellar clouds, the density can be higher, allowing new stars to form over time. In other areas, especially the vast voids between galaxies, matter is even more thinly spread. Despite this low density, these particles can still play important roles in astrophysical processes, such as the propagation of light and the formation of cosmic structures. Space, therefore, is not truly empty but filled with a very thin distribution of matter and energy. A neutron star is what remains after a massive star collapses under its own gravity, compressing matter to an extreme state that is almost impossible to imagine. In this environment, atoms are crushed so tightly that electrons and protons merge into neutrons, removing nearly all empty space. The result is one of the densest forms of matter in the universe. To put this into perspective, just a single teaspoon of neutron star material would weigh around 10 million tons if it were brought to Earth. That is roughly the mass of a mountain compressed into something you could hold in your hand. Despite being only about 20 kilometers across, neutron stars can contain more mass than the Sun. Their gravity is so intense that it bends light and distorts time around them. This extreme density shows how far the laws of physics can be pushed under the right conditions. But while neutron stars represent matter compressed to its limits, the space between celestial objects tells a very different story. Space is often described as a vacuum, but it is not completely empty. Even in the vast regions between stars and galaxies, there are still a few particles scattered throughout. On average, space contains about 5 hydrogen atoms per cubic meter. Compared to Earth's atmosphere, which is filled with trillions of molecules in the same volume, this is incredibly sparse. Yet, it is not nothing. These atoms are remnants of cosmic processes, left over from the Big Bang and from the life cycles of stars. In some regions, such as nebulae, this matter becomes dense enough to form new stars over millions of years. In others, like the enormous voids between galaxies, it becomes even thinner. This faint presence of matter plays a role in how light travels and how structures in the universe evolve over time. It reminds us that even empty space still holds traces of the universe's history, and within that space, light carries stories that began long before it ever reaches us. When you look at the Sun, the light reaching your eyes has traveled for about 8 minutes across the vacuum of space. This journey seems quick, but it is only the final step of a much longer process. The energy that becomes sunlight is created deep within the Sun's core through nuclear fusion, where hydrogen atoms combine to form helium. From that moment, the energy begins a slow and chaotic journey outward. Inside the Sun, photons do not move in straight lines. Instead, they are constantly absorbed and re-emitted by particles in a dense, turbulent environment. This process, known as a random walk, can take up to 100,000 years before the energy finally reaches the Sun's surface. Only then does it escape into space, traveling directly to Earth in minutes. This means the sunlight warming your skin today began its journey long before human civilization even existed. At the smallest scale, the human body is far less solid than it appears. Every atom that makes up your body and everything around you is mostly empty space. The nucleus at the center of an atom is incredibly tiny compared to the space occupied by its surrounding electrons. If all that empty space were removed and the remaining matter compressed together, the result would be astonishing. Every human on Earth, over 8 billion people, could fit into a volume roughly the size of a sugar cube. This is not because we are small, but because atoms are mostly void held together by forces rather than packed matter. The solidity you feel when you touch an object comes from electromagnetic interactions, not from particles physically colliding. This idea completely changes how we think about matter. What seems dense and continuous is actually structured emptiness at a deeper level. It shows that reality, as we perceive it, is built on invisible forces and spacing we never directly experience. And while matter itself is mostly empty, the universe is still filled with something far older and more persistent. Long after the beginning of the universe, traces of its origins still exist all around us. These traces come in the form of photons released shortly after the Big Bang, when the universe cooled enough for light to travel freely for the first time. Over billions of years, as the universe expanded, these photons stretched and lost energy, shifting from visible and infrared light into the microwave range. Today, they form what is known as the cosmic microwave background radiation, a faint glow that fills the entire universe. This radiation is not coming from any single direction, it is everywhere, a uniform echo of the universe's earliest moments. By studying tiny variations in this background, scientists can learn about the structure and evolution of the cosmos. It is essentially a snapshot of the universe when it was only a few 100,000 years old. And while this ancient light travels endlessly through space, the environment it moves through can create unexpected interactions. In the vacuum of space, materials behave in ways that are very different from what we experience on Earth. One of the most surprising examples is a process called cold welding. When two pieces of the same metal come into contact in space, they can bond together permanently without heat or melting. On Earth, this does not happen because surfaces are covered with thin layers of air, moisture, and contaminants that prevent direct atomic contact. In space, however, these layers are absent. If two clean metal surfaces touch, their atoms can align and share electrons, effectively merging into a single piece. This bond can be as strong as if the metal had been welded using high temperatures. Near a black hole, the very nature of time begins to change. According to Einstein's theory of relativity, gravity is not just a force, it is a bending of space and time itself. The stronger the gravity, the more time slows down. Around a black hole, where gravity is extreme, this effect becomes dramatic. To an outside observer, a clock near the black hole would appear to tick slower and slower as it gets closer to the event horizon, the boundary beyond which nothing can escape. In theory, if you were watching someone fall into a black hole, you would never actually see them cross that boundary. They would appear to slow down and fade away. But for the person falling in, time would feel completely normal. This difference in perception shows that time is not universal, but relative, depending on where you are and how strong gravity is around you. It transforms black holes from simple objects into places where the fundamental rules of reality begin to stretch. And as strange as time becomes near a black hole, the mathematics describing them leads to even more astonishing possibilities. When we think about complexity, few things seem as vast as the number of possible chess games. The combinations of moves are so enormous that they exceed the number of atoms in the observable universe. Yet even this staggering number is still smaller than the number of possible quantum states associated with a black hole. Black holes are not just simple objects, they contain an immense amount of information encoded on their surface, known as the event horizon. According to modern physics, this information is tied to entropy, a measure of how many different ways a system can be arranged. The larger the black hole, the more possible states it can have. This means that a black hole can store an almost unimaginable amount of information, far beyond anything we encounter in everyday life. It suggests that black holes are not just empty voids, but incredibly complex systems. And while their internal complexity is vast, their physical size can be surprisingly small. If the sun were somehow compressed into a black hole, it would not remain the same size. Instead, all of its mass would be squeezed into a region only about 6 kilometers across. This size is known as the Schwarzschild radius, the point at which gravity becomes so strong that not even light can escape. Despite containing the entire mass of the sun, the resulting black hole would be smaller than a city. This shows how extreme gravitational collapse can be, turning something enormous into something incredibly compact. The density would be so high that the concept of normal matter no longer applies. Space itself would be curved sharply around this tiny region, creating a boundary that separates the observable universe from the unknown interior. This contrast between immense mass and tiny size is one of the defining features of black holes. At the heart of some of the universe's most extreme objects lies a fundamental rule of quantum physics known as the Pauli exclusion principle. This principle states that no two electrons can occupy the same quantum state at the same time. In everyday life, this rule quietly shapes the structure of atoms and matter, but under extreme conditions, its effects become dramatic. In a neutron star, where matter has been compressed to incredible densities, particles are forced closer and closer together. As gravity tries to squeeze the star further, the Pauli exclusion principle creates a kind of resistance known as degeneracy pressure. This pressure prevents particles from being forced into identical states, effectively pushing back against the crushing force of gravity. Without it, neutron stars would continue collapsing indefinitely. This shows how a tiny quantum rule, operating at the smallest scales, can determine the fate of entire stars. And while the laws of physics create stability in such extreme environments, planetary motion can produce equally surprising effects closer to home. On the surface of Venus, time behaves in a way that feels almost counterintuitive. Venus rotates extremely slowly, taking about 243 Earth days to complete a single rotation on its axis. However, it orbits the Sun faster than it rotates, completing one full orbit in about 225 Earth days. This means that a single day on Venus, defined as one full rotation, is actually longer than its entire year. If you were standing on Venus, you would experience a year passing before the planet even finished one full spin. This unusual relationship between rotation and orbit challenges our everyday understanding of time, where days are always shorter than years. It highlights how planetary motion can vary widely across the solar system. And as strange as Venus's sense of time is, the direction in which it spins adds another layer of mystery. Unlike most planets in the solar system, which rotate in the same direction they orbit the Sun, Venus spins in the opposite direction. This is known as retrograde rotation. As a result, the Sun on Venus would appear to rise in the west and set in the east, the reverse of what we experience on Earth. The reasons behind this unusual rotation are still not fully understood, but scientists believe it may be linked to massive collisions early in the planet's history or long-term gravitational interactions with the Sun's atmosphere. This backward spin, combined with its extremely slow rotation, makes Venus one of the most unique planets in the solar system. On Mercury, time behaves in a way that feels almost impossible at first glance. Mercury rotates very slowly, taking about 59 Earth days to complete one full spin on its axis. However, because of the way its rotation and orbit interact, a resonance known as a 3-to-2 spin-orbit relationship, a full solar day, from one sunrise to the next, takes about 176 Earth days. At the same time, Mercury completes an orbit around the Sun in just 88 Earth days. This means that a single day on Mercury lasts longer than its entire year. If you were standing on its surface, you would watch the Sun move across the sky so slowly that seasons would pass before one full day was complete. This strange relationship between rotation and orbit highlights how different planetary motion can be compared to Earth. And while Mercury bends our understanding of time, other planets display powerful forces that shape their atmospheres in dramatic ways. Deep within the swirling atmosphere of Jupiter lies one of the most iconic features in the solar system, the Great Red Spot. This massive storm has been raging for at least 350 years, making it one of the longest-lasting weather systems ever observed. Large enough to swallow Earth, it is a high-pressure storm spinning in Jupiter's thick clouds, fueled by the planet's immense energy and rapid rotation. Unlike storms on Earth, which lose strength when they pass over land, Jupiter has no solid surface to disrupt it. Instead, the storm feeds off surrounding atmospheric currents, allowing it to persist for centuries. Its deep red color and enormous scale make it visible even through small telescopes from Earth. The Great Red Spot shows how weather can become a permanent feature under the right conditions. And while Jupiter's atmosphere is defined by enduring storms, other planets exhibit even stranger physical orientations. Uranus stands out as one of the most unusual planets because of its extreme axial tilt. Instead of spinning upright like Earth, Uranus is tilted at about 98 degrees, meaning it essentially rotates on its side. As it orbits the Sun, it appears to roll along its path, rather than spin like a top. This tilt causes extreme seasonal changes, where each pole can face the Sun continuously for decades, before plunging into long periods of darkness. Scientists believe this unusual orientation may have been caused by a massive collision early in the planet's history. Uranus challenges our idea of what a normal planet should look like. And while its rotation is unusual, another distant planet takes atmospheric extremes to an entirely different level. On Neptune, the winds are the fastest known anywhere in the solar system. Speeds can reach up to 2,100 kilometers per hour, far exceeding even the most powerful storms on Earth. What makes this especially surprising is that Neptune is located far from the Sun and receives very little solar energy. Despite this, its atmosphere remains incredibly dynamic and violent. Scientists believe that internal heat rising from the planet's interior may help drive these extreme winds. Dark storm systems, similar to Jupiter's Great Red Spot, form and disappear over time, carried by these powerful currents. Neptune demonstrates that distance from the Sun does not necessarily mean calm conditions. In fact, it can host some of the most intense weather in the solar system. On Mars stands the largest volcano in the solar system, Olympus Mons. This immense shield volcano rises about 22 kilometers above the Martian surface, nearly 3 times the height of Mount Everest. But what truly makes Olympus Mons extraordinary is its width. Stretching over 600 kilometers across, it is so vast that if you stood at its base, you wouldn't be able to see the summit. In fact, even from the center, the edges curve away with the planet's horizon, making the volcano feel more like an entire landscape than a single mountain. Its enormous size is partly due to Mars having lower gravity than Earth, allowing lava to spread farther and build up over time without collapsing. Unlike Earth, Mars also lacks active plate tectonics, meaning the volcano remained in one place and continued to grow for millions of years. Olympus Mons shows how planetary conditions can produce structures far beyond anything we see on Earth. And while Mars showcases extremes in size, another planet reveals surprising contrasts in structure. Encircling Saturn are some of the most iconic features in the solar system: its rings. From a distance, they appear thick and solid, like giant disks of ice and rock. However, up close they are incredibly thin. On average, Saturn's rings are only about 10 to 30 meters thick, yet they stretch over 282,000 kilometers in width. This means that compared to their vast horizontal spread, they are almost paper thin. The rings are made up of countless particles, ranging in size from tiny grains to large chunks of ice, all orbiting Saturn in a delicate balance. Their thinness is maintained by gravitational interactions, both with Saturn itself and with small moons embedded within the rings. This creates intricate patterns, gaps, and waves across their structure. Saturn's rings highlight how something can be both enormous and fragile at the same time. And beyond their structure, Saturn itself holds another surprising physical property. Despite being one of the largest planets in the solar system, Saturn is actually less dense than water. This means that, in theory, if there were a body of water large enough, Saturn would float. Its low density comes from its composition. It is primarily made of hydrogen and helium, the lightest elements in the universe. Unlike rocky planets such as Earth or Mars, Saturn does not have a solid surface in the traditional sense. Instead, its interior transitions from gas to liquid under immense pressure. This unique composition gives Saturn its relatively low mass for its size compared to other planets. On Mercury, temperatures can reach scorching extremes during the day. Yet at its poles, something completely unexpected exists: ice. Deep within craters that never receive sunlight, temperatures remain permanently low. These regions are in constant shadow because Mercury has almost no tilt, meaning sunlight never reaches the bottoms of certain polar craters. As a result, These areas act like natural cold traps, preserving water ice for billions of years. This ice likely arrived through comet impacts or water-rich asteroids, settling into these shadowed regions where it could not evaporate away. The idea that the closest planet to the Sun can harbor frozen water challenges our assumptions about where ice can exist. It shows that temperature in space is not just about distance from the Sun, but also about light exposure and planetary geometry. And while Mercury hides ice in darkness, far beyond it lies a world defined by a unique gravitational relationship. Out in the distant reaches of the solar system, Pluto and its largest moon, Charon, share a remarkable bond. They are tidally locked to each other, meaning the same side of Pluto always faces Charon, and the same side of Charon always faces Pluto. This is different from Earth and its moon, where only the moon is tidally locked. In this case, both bodies are locked together in a gravitational dance. If you stood on Pluto, Charon would appear fixed in the sky, never rising or setting. This mutual locking happens because both bodies are relatively close in size, allowing their gravitational forces to influence each other equally over time. It creates a stable system where rotation and orbit are perfectly synchronized. This unique relationship highlights how gravity can shape motion in precise and predictable ways. And while Pluto and Charon show balance, the largest planet in the solar system reveals something entirely different. On Jupiter, there is no solid surface you could stand on. Instead, the planet is composed mostly of hydrogen and helium, transitioning gradually from gas at the top to liquid deeper down under immense pressure. If you were to descend into Jupiter, you would not land. You would continue sinking through thicker and denser layers of atmosphere. As you go deeper, the pressure and temperature increase dramatically, eventually turning the hydrogen into a metallic state where it behaves like an electrical conductor. There is no clear boundary between surface and interior, only a continuous transition. This makes Jupiter fundamentally different from rocky planets like Earth or Mars. Orbiting Mars are two small, irregularly shaped moons, Phobos and Deimos, but it is Phobos that reveals just how strange low gravity can be. Phobos is so small that its gravitational pull is only about 1,000th of Earth's. This means that if you were standing on its surface, even a gentle throw could send an object into orbit around the moon. Walking there would feel more like floating, where a single jump could launch you high above the surface. Because of this weak gravity, Phobos cannot hold on to loose material very tightly, giving it a surface covered in fine dust and debris. It also orbits extremely close to Mars, completing a full orbit in just over 7 hours, making it one of the fastest orbiting moons in the solar system. This fragile balance between motion and gravity shows how different celestial environments can be. And while Phobos demonstrates how weak gravity can be, deeper in the solar system, pressure reaches unimaginable extremes. At the heart of Neptune, conditions are so extreme that familiar materials behave in unfamiliar ways. Deep beneath its thick atmosphere, pressure rises to millions of times that of Earth's surface. Under these conditions, carbon atoms are squeezed so tightly that they can form diamonds. Scientists believe that these diamonds may not just exist as solid structures, but could melt into a strange, dense liquid, forming what is sometimes described as a diamond ocean. In this environment, intense heat and pressure combine to create states of matter that cannot exist naturally on Earth. These processes may even lead to diamond rain, where solid diamond forms and sinks deeper into the planet's interior. Neptune shows how different the chemistry of planets can become under extreme pressure. And while Neptune's interior represents one extreme, Earth holds a unique distinction of its own. Among all the planets in the solar system, Earth is the densest. This might seem surprising, especially when compared to massive gas giants like Jupiter or Saturn. However, density is not about size, it is about how much mass is packed into a given volume. Earth's high density comes from its composition, which includes heavy elements like iron and nickel concentrated in its core. During the planet's formation, heavier materials sank inward, while lighter materials rose to the surface, creating a layered structure. This dense core plays a crucial role in generating Earth's magnetic field, which protects the planet from harmful solar radiation. Earth's density highlights how composition, not just size, defines a planet's physical properties. At the core of Sun, an extraordinary process is constantly unfolding. Through nuclear fusion, hydrogen atoms are combined to form helium, releasing enormous amounts of energy in the process. But this energy does not come from nowhere, it comes from mass itself. Every second, the Sun converts about 4 million tons of its own mass into energy, as described by Einstein's famous equation, E=mc². This energy radiates outward, eventually reaching Earth as light and heat. Despite losing such a vast amount of mass every second, the Sun is so massive that this loss has only a very small effect over its lifetime. It will continue shining for billions of years before running out of fuel. This constant conversion of mass into energy is what powers life on Earth and drives the entire solar system. And while the Sun behaves in a predictable and stable way, not all stars follow such consistent patterns. Far beyond our solar system lies a star known as KIC 8462852, often referred to as Tabby's star. What makes this star unusual is the way its brightness changes over time. Unlike most stars, which dim in regular patterns due to orbiting planets or natural cycles, this star shows irregular and unpredictable dips in brightness. At times, it can lose a significant portion of its light, only to return to normal without a clear explanation. Scientists have proposed various theories, including clouds of dust, fragments of comets, or debris from a disrupted planetary system passing in front of the star. Despite ongoing study, no single explanation fully accounts for all the observations. This makes Tabby's star one of the most intriguing mysteries in modern astronomy. It reminds us that even with advanced technology, there are still phenomena in the universe that challenge our understanding. And while some stars behave unpredictably, others are defined by their immense size. One of the most famous examples of a giant star is Betelgeuse, located in the constellation Orion. Betelgeuse is a red supergiant, meaning it has expanded to an enormous size as it nears the end of its life. If it were placed at the center of our solar system, its outer layers would extend beyond the orbit of Jupiter. This means it would engulf Mercury, Venus, Earth, Mars, and even the asteroid belt. Despite its immense size, Betelgeuse is not as dense as the Sun. Its material is spread out over a much larger volume, giving it a relatively low density. Its surface appears dim and reddish compared to hotter stars, reflecting its cooler temperature. Betelgeuse demonstrates how stars can evolve into vastly different forms over time, growing from stable, sun-like stars into enormous giants that dominate their surrounding space. When we try to grasp the scale of the universe, comparisons become the only way to make sense of it. One of the most striking is this. There are more stars in the observable universe than grains of sand on all of Earth's beaches combined. Every grain of sand you can imagine across deserts, coastlines, and shores worldwide would still be outnumbered by the stars scattered across galaxies. Scientists estimate that there are hundreds of billions of galaxies, each containing hundreds of billions of stars. When multiplied together, the total becomes almost impossible to comprehend. This comparison is not just poetic, it reflects the true scale of the cosmos. It shows that what feels vast on Earth is tiny when placed against the backdrop of the universe. And within that immense population of stars, some behave in ways that push the limits of physics itself. Among the most extreme of these are neutron stars, collapsed remnants of massive stars that pack enormous mass into a tiny space. Some neutron stars rotate at incredible speeds, with the fastest known spinning up to 716 times per second. These rapidly spinning neutron stars are called pulsars. As they rotate, they emit narrow beams of radiation, including radio waves from their magnetic poles. If these beams are aligned just right, they sweep across Earth like a lighthouse beam, appearing as regular pulses of energy. This precise and rapid rotation makes pulsars some of the most accurate natural clocks in the universe. Their stability allows scientists to use them to study gravity, space-time, and even detect gravitational waves. Pulsars demonstrate how extreme conditions can create remarkably precise systems. And while some stars are defined by their speed and energy, others are defined by their incredible age. One of the oldest known stars is HD 140283, often nicknamed the Methuselah star. It is estimated to be about 13.7 billion years old, making it nearly as old as the universe itself, which is about 13.8 billion years old. This means it formed very early in cosmic history, not long after the first stars began to appear. Located relatively close to Earth in astronomical terms, this star provides a glimpse into the early universe. Its composition contains very few heavy elements, indicating it formed before many of the processes that enrich stars with heavier materials had fully developed. Studying such ancient stars helps scientists understand how the universe evolved over time. When stars like our Sun reach the end of their lives, they do not explode, they shrink. What remains is a dense, hot core known as a white dwarf. These stellar remnants no longer produce energy through fusion, so they slowly cool over time, radiating away their remaining heat. However, this cooling process is incredibly slow. It takes trillions of years for a white dwarf to fade completely into what scientists call a black dwarf, a cold, dark remnant that emits no visible light. The reason we have never observed a black dwarf is simple. The universe itself is not old enough. At about 13.8 billion years old, it hasn't existed long enough for any white dwarf to fully cool down. This means that every white dwarf we see today is still glowing, carrying leftover heat from its past life as a star. It gives us a glimpse into a future universe that has not yet arrived. And while some stars fade slowly over unimaginable timescales, others meet far more sudden and dramatic ends. Not all stars follow the same path when they die. Some of the most massive stars in the universe take a shortcut through their final stages. Instead of exploding in a supernova, they collapse directly into black holes. In these cases, the star's core becomes so massive that not even the outward pressure of a supernova can stop the collapse. Gravity overwhelms everything, pulling the star inward until it forms a black hole almost instantly. This process can be surprisingly quiet compared to the explosive deaths of other stars, sometimes producing little visible light at all. These direct collapses are thought to be one way some of the universe's largest black holes form. They show that even the most energetic stars can end their lives in silence. And while some stars collapse alone, others exist in pairs, where their fates become tightly linked. In binary star systems, where two stars orbit each other, a very different kind of stellar death can occur. If one of the stars is a white dwarf, it can begin to pull material from its companion through gravity. This stolen matter accumulates on the white dwarf surface over time. As more and more material builds up, the pressure and temperature increase until a critical point is reached. When this limit is exceeded, a runaway nuclear reaction ignites, causing a powerful explosion known as a Type Ia supernova. Unlike other supernovae, these explosions are remarkably consistent in brightness, making them useful tools for measuring distances across the universe. Type Ia supernovae have even helped scientists understand the expansion of the universe. Among the many strange stars scattered across the galaxy, Przybylski's star stands out as one of the most mysterious. When scientists studied its light, they found signatures of elements that are extremely unstable, elements that, under normal conditions, should decay almost instantly and not exist in detectable amounts. These include rare heavy elements that typically require intense environments, such as nuclear reactions in stars or supernovae, to form. Yet in this star, they appear to persist. This has led to several theories. One possibility is that unknown nuclear processes inside the star are continuously creating these elements. Another idea suggests that they may be produced through interactions with high-energy particles or decay chains happening within the star itself. However, none of these explanations fully solve the mystery. Przybylski's star challenges our understanding of how elements form and behave, suggesting that there may still be processes in the universe we do not yet fully understand. And while this star reveals mysteries at the level of atomic physics, the structure of the universe itself presents even larger scale puzzles. When we look out into space, we are also looking back in time. The observable universe, the portion we can see, is estimated to be about 93 billion light-years in diameter. At first, this seems impossible, because the universe is only about 13.8 billion years old. If nothing can travel faster than light, how can we see something so far away? The answer lies in the expansion of space itself. After the Big Bang, space did not remain static, it expanded, and in some periods, it expanded extremely rapidly. As light traveled through this expanding space, the distance between objects grew, stretching the universe far beyond what simple calculations would suggest. This means the light we see today has traveled for billions of years, but the objects it came from are now much farther away than the distance the light originally covered. This expansion reshapes how we understand distance and time. And as space continues to stretch, it creates another surprising effect. Because the universe is expanding, most galaxies are moving away from us, and many are doing so at speeds that exceed the speed of light. At first, this might seem to violate the laws of physics, but it does not. The key is that these galaxies are not moving through space faster than light. Rather, the space between us and them is expanding. As a result, distant galaxies are carried away as the fabric of the universe stretches. The farther away a galaxy is, the faster it appears to recede. This effect becomes so extreme at great distances that some galaxies are moving away faster than light, meaning the light they emit today will never reach us. These regions are effectively beyond our observable horizon. This shows that the universe is not just vast, but also dynamic, constantly changing on the largest scales. Time is not as constant as it feels. Even here on Earth, it flows at slightly different rates depending on where you are. Because of gravitational time dilation, time moves a tiny bit slower in stronger gravitational fields. This means that your feet, being slightly closer to Earth's center of mass, experience a stronger gravitational pull than your head. As a result, time passes ever so slightly slower at your feet than at your head. The difference is incredibly small, far too small to notice in daily life, but it is measurable with precise instruments. This effect is not just theoretical. It has been confirmed through experiments and is even accounted for in technologies like GPS satellites. It reveals that time is not a universal constant ticking the same everywhere, but something that can stretch and shift depending on gravity. And while this difference is subtle on Earth, it becomes more noticeable when we leave the planet. Aboard the International Space Station, astronauts experience time slightly differently than people on Earth. Because the ISS moves at extremely high speeds, about 28,000 kilometers per hour, time for the astronauts slows down due to a form of time dilation predicted by Einstein's theory of relativity. Over the course of a year, this effect causes astronauts to age about 0.007 seconds less than people on Earth. It is a tiny difference, but it is real and measurable. This means that astronauts are, in a very literal sense, traveling slightly into the future compared to those on the ground. This effect shows how both gravity and motion can influence time. And while time can bend under these conditions, the origin of time itself begins in an even more surprising way. The beginning of the universe is often imagined as an explosion from a single point, but that picture is not quite accurate. The Big Bang did not happen at one location in space, it happened everywhere at once. At the moment of the Big Bang, space itself was compressed into an extremely hot and dense state. When expansion began, it was not matter moving outward into empty space, but space itself stretching in all directions. This means that every point in the universe today can be traced back to that same initial state. There is no central location where the Big Bang occurred, and no edge from which it expanded. Instead, the entire universe expanded uniformly, with every region moving away from every other region. This idea challenges our everyday understanding of explosions in space, showing that the universe did not expand into something, it created space as it expanded. As we look deeper into the universe, we begin to encounter limits not just of distance, but of what can ever be known. Because the universe is expanding, there are regions so far away that their light will never reach us, no matter how long we wait. This is not just because they are distant, but because space itself is stretching faster and faster over time. In these regions, galaxies are being carried away at such speeds that even light cannot bridge the gap. This creates what is known as a cosmic horizon, beyond which events are permanently hidden from us. Even in infinite time, signals from those regions will never arrive. It means that there are parts of the universe that are fundamentally unreachable, not just physically, but observationally. This idea reshapes our understanding of the cosmos, showing that what we can see is only a fraction of what exists. And as we try to map the universe, another surprising truth emerges about its structure. Unlike an explosion in space that expands from a central point, the universe itself has no center. The Big Bang did not occur at a specific location that everything is moving away from. Instead, space itself expanded uniformly in all directions. This means that from any point in the universe, it appears as though everything else is moving away. If you were in a distant galaxy, you would see the same pattern we observe from Earth galaxies receding in every direction. This can be compared to points on the surface of an inflating balloon, where every point moves away from every other point as the surface expands. There is no special center on the surface itself. This idea challenges our intuition, as we are used to thinking of expansion as something that happens outward from a specific place. But in the universe, expansion happens everywhere at once, and driving this expansion is one of the greatest mysteries in modern physics. The force behind the accelerating expansion of the universe is known as dark energy. Despite making up a large portion of the universe, dark energy remains one of the least understood aspects of physics. It does not emit light, cannot be directly observed, and its true nature is still unknown. What scientists do know is that it acts in opposition to gravity, pushing space apart and causing the expansion of the universe to speed up over time. This discovery was unexpected, as it was once believed that gravity would eventually slow the expansion. Instead, observations showed the opposite, that galaxies are moving away from each other faster and faster. Dark energy highlights how much of the universe remains unexplained, reminding us that even as we uncover more about the cosmos, some of its most fundamental forces are still beyond our full understanding. If the universe is truly infinite, then the implications become almost impossible to fully grasp. In an infinite cosmos, matter is spread out endlessly, but the number of ways atoms can arrange themselves is still finite. This leads to a strange conclusion. Given enough space, those same arrangements must repeat. That means somewhere, unimaginably far away, there could be another version of you built from the same atoms, living a nearly identical life. And not just one version, but infinitely many, each differing by tiny details. In one, you made a slightly different decision. In another, events unfolded in a completely different way. This idea is not science fiction, but a logical outcome of combining infinity with the laws of physics. It challenges our sense of uniqueness and identity, suggesting that what we experience may be just one of countless variations. While we may never observe these distant copies, the possibility reshapes how we think about existence itself. And while infinity stretches beyond imagination, astronomers are still pushing the limits of what we can actually observe. One of the most distant known objects ever detected is a galaxy called HD1. This galaxy is located about 13.5 billion light-years away, meaning the light we see from it today began its journey when the universe was still very young, only about 330 million years after the Big Bang. Observing such distant objects is like looking back in time, allowing scientists to study the earliest stages of galaxy formation. At that time, the universe was very different from what we see today, filled with the first generations of stars and galaxies. Discoveries like HD1 push the limits of current technology and help refine our understanding of how the universe evolved. Each distant object acts as a window into the past, revealing how structure gradually emerged from the aftermath of the Big Bang. And while we can observe distant galaxies through light that has traveled billions of years, some forms of life show resilience in environments far closer to home. Among the most resilient life forms known are tardigrades, often called water bears. These microscopic creatures have demonstrated an extraordinary ability to survive extreme conditions, including the vacuum of space. In experiments, tardigrades have been exposed to intense radiation, extreme temperatures, and complete dehydration. Yet many were able to recover and continue living once returned to normal conditions. Their survival is made possible by a unique state called cryptobiosis, in which their metabolism nearly stops, allowing them to endure environments that would be fatal to most life forms. They can lose almost all of their body water and still revive later. Tardigrades show that life can persist under conditions far beyond what we typically consider habitable. In the vast, cold regions between stars, enormous clouds of gas and dust known as nebulae quietly drift through space. These nebulae are not just empty clouds, they are active chemical environments where complex reactions take place over millions of years. Scientists have discovered that under the right conditions, simple atoms within these clouds can combine to form complex organic molecules, including the building blocks of life. Radiation from nearby stars, shockwaves from stellar explosions, and interactions between particles all contribute to these chemical processes. This means that the ingredients for life may not be limited to planets, but could form naturally in space itself, long before planets even exist. These molecules can then become part of new star systems, carried into planets, moons, and comets. It suggests that the chemistry of life might be widespread throughout the universe, waiting for the right conditions to develop further. And as we study these cosmic clouds more closely, we begin to find direct evidence of this process. One of the most significant discoveries supporting this idea is the detection of glycine in interstellar space. Glycine is the simplest amino acid, a fundamental component used by living organisms to build proteins. Scientists have identified its unique chemical signature in regions of space far from Earth, confirming that at least some of life's essential molecules can form naturally outside of planets. This discovery is important because it shows that the basic ingredients for life are not exclusive to Earth. Instead, they may be scattered throughout the galaxy, embedded in gas clouds, comets, and planetary systems. While finding glycine does not mean life exists elsewhere, it strengthens the possibility that the conditions needed for life could arise in many places. It bridges the gap between chemistry and biology on a cosmic scale. And while these molecules form in distant clouds, closer to home, some worlds may already contain the environments needed to support life. Beneath the frozen surface of Europa lies one of the most intriguing environments in the solar system. Europa is covered by a thick shell of ice, but beneath that shell is believed to be a vast, global ocean of liquid water. This ocean may contain more water than all of Earth's oceans combined. Despite being far from the Sun, Europa's interior is kept warm by gravitational forces from Jupiter, which create tidal heating inside the Moon. This heat prevents the water beneath the ice from freezing solid. The presence of liquid water, combined with potential chemical energy from the Moon's interior, makes Europa one of the most promising places to search for life beyond Earth. The question of whether we are alone in the universe has led scientists to develop ways of estimating the possibility of other civilizations. One of the most famous attempts is the Drake equation, which combines factors such as the rate of star formation, the number of planets, and the likelihood of life developing and becoming intelligent. Depending on how these variables are estimated, the equation suggests that there could be thousands of communicating civilizations within the Milky Way galaxy alone. Yet, despite this possibility, we have not detected any clear signals or evidence of extraterrestrial intelligence. This contradiction is often referred to as the Great Silence, or the Fermi Paradox. It raises profound questions. Are civilizations rare, short-lived, or simply too far away to detect? The Drake equation does not provide a definitive answer, but it frames the mystery in a scientific way, showing that the universe could be filled with life, even if we have not yet found it. And while intelligent life remains uncertain, evidence suggests that simpler conditions for life may have existed much closer to home. On Mars, there is strong evidence that liquid water once flowed across its surface. Ancient river valleys, lake beds, and mineral deposits all point to a time when Mars had a warmer and wetter climate. Scientists believe that this period may have lasted for billions of years longer than it took for complex life to evolve on Earth. During that time, Mars may have had conditions suitable for microbial life, including liquid water, a thicker atmosphere, and chemical nutrients. Over time, however, the planet lost much of its atmosphere, causing temperatures to drop and water to either freeze or escape into space. Today, Mars is cold and dry, but traces of its watery past remain etched into its surface. This history makes Mars one of the most important targets in the search for past life. And while Mars shows that habitable conditions once existed, other worlds may still hold them today. One of the most promising examples is Enceladus, a small moon orbiting Saturn. Beneath its icy surface lies a hidden ocean, and from cracks near its south pole, plumes of water vapor shoot out into space. These plumes have been directly sampled by spacecraft, revealing not just water, but also organic compounds and hydrogen. This combination is particularly important because it represents the key ingredients needed for life as we understand it: liquid water, organic molecules, and a potential energy source. The hydrogen suggests that chemical reactions similar to those found in Earth's deep-sea hydrothermal vents may be occurring within Enceladus. During the early era of space exploration, an unexpected discovery raised new questions about the resilience of life beyond Earth. In 1967, a robotic probe called Surveyor 3 landed on the Moon. 2.5 years later, astronauts from Apollo 12 visited the site and brought parts of the probe back to Earth for analysis. To the surprise of scientists, some microorganisms were reportedly found to have survived the harsh conditions of space during that time. These conditions included exposure to vacuum, extreme temperature swings, and radiation. While the exact interpretation of the findings has been debated, the idea that life could endure such an environment sparked serious interest in the possibility of organisms surviving beyond Earth. It suggested that life, under certain conditions, might be far more durable than previously thought. And as scientists began to take planetary contamination more seriously, they discovered that some microbes were already adapting in unexpected ways. Even here on Earth, in the sterile environments where spacecraft are assembled, microorganisms have shown a remarkable ability to survive. In clean rooms designed to eliminate contamination, bacteria are exposed to powerful disinfectants, radiation, and strict environmental controls. Yet some of these microbes not only survive, but evolve resistance to the very measures meant to destroy them. These bacteria adapt over time, developing mechanisms that allow them to withstand extreme cleaning processes. This resilience presents a challenge for space missions, as even a small number of surviving organisms could be carried to other planets. It highlights how life can adapt to extreme environments, even those engineered to prevent it. And while microbes can survive in controlled environments, natural processes on Earth may also send life beyond our planet. Every year, Earth is struck by countless small asteroids and meteoroids. When these impacts occur with enough force, they can eject material from Earth's surface into space. Scientists estimate that about 1 billion kilograms of rocky material is blasted into space annually through these events. Some of this debris may eventually travel to other planets or moons. If microorganisms are present within these rocks, they could potentially survive the journey, protected from radiation and vacuum by the surrounding material. This process, known as panspermia, suggests that life could spread naturally between worlds. It raises the possibility that life on Earth may have originated elsewhere, or that Earth itself could seed life on other planets. When humans leave Earth and enter microgravity, even the structure of the body begins to change. One of the most noticeable effects is an increase in height. Astronauts can grow up to 5 centimeters taller while in space. This happens because, on Earth, gravity constantly compresses the spine, keeping the discs between the vertebrae slightly flattened. In the weightlessness of space, that adduct is removed, allowing the spine to fully extend. The discs expand, and the body straightens, leading to a temporary increase in height. However, this change is not permanent. Once astronauts return to Earth, gravity compresses the spine again, and their height gradually returns to normal. This simple physical change highlights how deeply gravity influences the human body, even in ways we rarely notice. And while the spine adjusts to weightlessness, other parts of the body respond in ways that feel far less comfortable. In the first few days of living in microgravity, astronauts often experience a strange and uncomfortable sensation known as fluid shift. Without gravity pulling bodily fluids downward, blood and other fluids redistribute toward the upper body and head. This creates a feeling of constant congestion, as if having a blocked nose or a mild cold. The face may appear slightly puffy, while the legs can look thinner due to reduced fluid volume. This shift can also affect vision and balance as the body adjusts to its new environment. Over time, the body begins to adapt, but the initial phase can be disorienting. This effect shows how gravity plays a crucial role in regulating circulation and fluid balance. And while the human body adjusts to life in orbit, the space surrounding Earth is becoming increasingly crowded. Orbiting the planet is a growing cloud of human-made debris, remnants of satellites, fragments from collisions, and pieces of old spacecraft. Scientists track more than 27,000 of these objects, and many are traveling at speeds of around 28,000 kilometers per hour. At such velocities, even a tiny fragment can cause serious damage if it collides with a spacecraft or satellite. This debris forms a hazardous environment for missions in low Earth orbit, including those involving the International Space Station. Space agencies must constantly monitor and track these objects to avoid collisions, sometimes even adjusting spacecraft orbits to stay safe. This growing cloud of debris highlights a new challenge of the space age. While space may seem vast and empty, the region around Earth is becoming increasingly crowded and complex. In 1971, during the Apollo 14 mission, astronaut Alan Shepard did something completely unexpected on the surface of the moon. He played golf. Using a makeshift club attached to a sampling tool, Shepard swung at 2 golf balls in the low-gravity environment. With only 1/6 of Earth's gravity pulling them down, and no air resistance to slow them, the balls traveled much farther than they would have on Earth. Shepard famously joked that one of them went miles and miles. Today, those golf balls are still there, resting undisturbed on the lunar surface. With no atmosphere, wind, or weather to move them, they could remain in place for millions of years. This moment stands as a unique blend of human curiosity and exploration, showing that even in one of the most extreme environments, people still find ways to connect with familiar experiences. And while these objects remain untouched on the moon, other instruments left behind continue to serve a scientific purpose. Among the most important tools left on the moon are retroreflectors, placed there by astronauts during multiple Apollo missions. These devices are specially designed mirrors that reflect light directly back to its source. Scientists on Earth use powerful lasers to send beams of light to these reflectors and measure how long it takes for the light to return. By calculating this travel time, they can determine the distance between Earth and the moon with incredible precision down to a few millimeters. This ongoing experiment has been running for decades, providing valuable data about the moon's orbit and how it is slowly drifting away from Earth over time. It is one of the longest-running scientific experiments ever conducted beyond our planet. And while the moon offers a stable platform for long-term experiments, life in orbit around Earth presents a completely different experience of time and motion. Aboard the International Space Station, astronauts experience a cycle of day and night far more rapidly than on Earth. The station orbits the planet at incredible speed, completing one full orbit approximately every 90 minutes. As a result, astronauts witness about 16 sunrises and 16 sunsets every single day. This constant transition between light and darkness can be disorienting, especially in the early stages of a mission. To maintain a regular routine, astronauts rely on strict schedules and artificial lighting to simulate a 2-4-hour day. This environment highlights how our sense of time is closely tied to the natural rhythms of Earth, and how quickly those rhythms can change when we leave the planet. After a spacewalk, astronauts returning to the International Space Station often notice something unexpected. Their suits carry a distinct smell. It has been described as hot metal, welding fumes, or even gunpowder. This scent is not coming from space itself, since space is a vacuum and cannot carry smells. Instead, it is caused by atomic oxygen, a highly reactive form of oxygen found in low Earth orbit. During a spacewalk, atomic oxygen interacts with the surface of the suit, altering materials at a microscopic level. When the astronaut re-enters the station and removes their helmet, these altered particles react with the oxygen-rich air inside, producing that sharp, metallic odor. It is a reminder that even in the emptiness of space, subtle chemical interactions are constantly taking place. And while space affects materials in surprising ways, it also changes how the human body behaves in ways we rarely experience on Earth. In microgravity, even something as simple as crying works differently. On Earth, gravity pulls tears downward, allowing them to flow off the face. In space, without gravity, tears do not fall. Instead, they collect and form a floating, wobbling sphere around the eye. Surface tension keeps the liquid together, causing it to cling to the skin rather than dripping away. If enough tears build up, they can blur vision or create discomfort until the astronaut wipes them away. This small but striking effect shows how deeply gravity influences everyday bodily functions. And while fluids behave differently around the eyes, the management of fluids aboard the station is taken to an entirely different level. One of the most advanced systems on the International Space Station is its water recycling system. In the closed environment of space, resources must be reused as efficiently as possible. The station's system is capable of converting about 90% of wastewater, including urine, sweat, and even moisture from the air, back into clean, drinkable water. This is achieved through a combination of filtration, chemical treatment, and distillation processes that remove impurities and contaminants. The result is water that meets strict safety standards for human consumption. While the idea may seem unusual at first, it is a critical part of sustaining long-term missions in space, where carrying large supplies of water is not practical. In microgravity, even the simplest bodily functions behave in unfamiliar ways. On Earth, when you burp, gas rises above liquid in the stomach due to gravity, allowing it to escape easily. But in space, aboard environments like the International Space Station, gas and liquid do not separate in the same way. Without gravity, everything mixes together, forming a uniform mass. As a result, astronauts cannot burp normally. Instead, when they try, they may experience what is informally called a wet burp, where small amounts of liquid come up along with the gas. This can be uncomfortable, and is one of the many adjustments astronauts must make when living in microgravity. It highlights how even the most automatic bodily processes rely on gravity to function properly. And while space changes how the body behaves, it also reshapes some of the most historic moments in human exploration. During the historic Apollo 11 mission, when humans first stepped onto the moon, even eating became a carefully planned activity. The first food consumed on the lunar surface was not a full meal, but small bacon cubes. These were part of the specially designed space food system, created to be compact, lightweight, and easy to consume in a low-gravity environment. Every item brought to the moon had to meet strict requirements, balancing nutrition, safety, and practicality. The bacon cubes may seem like a small detail, but they represent the beginning of human life beyond Earth, where even ordinary actions like eating had to be reimagined for an entirely new environment. And while Apollo 11 marked a major milestone, earlier missions carried their own hidden stories. When Yuri Gagarin became the first human to travel into space aboard the Vostok 1, his journey was a groundbreaking achievement. However, one detail was kept secret for years. During re-entry, Gagarin did not land inside his capsule. Instead, he ejected from it and parachuted safely back to Earth separately. This was done because the Vostok capsule was not designed to land softly with a person inside. At the time, international aviation records required that the pilot land with the craft for the flight to officially count. To ensure the mission's recognition, this detail was initially withheld. It was only later revealed, adding another layer to one of the most iconic moments in space history. Drifting at the edge of our solar system is one of humanity's most distant creations, Voyager 1. Launched in 1977, this spacecraft has traveled farther than any other human-made object, now over 23 billion kilometers away from Earth. Despite this unimaginable distance, it is still sending signals back to us, carrying data from interstellar space. Voyager 1 has crossed the boundary known as the heliopause, where the influence of the sun's solar wind fades and the environment of interstellar space begins. Its signals take over 20 hours to reach Earth, traveling at the speed of light. Even now, decades after its launch, it continues to function, powered by a slowly diminishing energy source. This small machine, built in the 1970s, is now humanity's farthest ambassador, silently moving through the darkness between stars. And while Voyager explores the emptiness beyond our solar system, some of the most extreme activity can be found much closer to home. Orbiting Jupiter is one of the most volcanically active worlds ever discovered. Io. Unlike Earth, where volcanic activity is limited to certain regions, Io's entire surface is constantly reshaped by eruptions. With over 400 active volcanoes, it is the most geologically active body in the solar system. This intense activity is driven not by internal heat alone, but by gravitational forces. As Io orbits Jupiter, it is stretched and squeezed by the planet's immense gravity, as well as by the gravitational pull of nearby moons. This process, known as tidal heating, generates enormous amounts of internal friction and heat, melting rock beneath the surface. The result is a landscape filled with lava flows, volcanic plumes, and constantly changing terrain. Io shows how gravity can act as a powerful energy source, driving processes that would otherwise require internal heat alone. And while Io is defined by fire and molten rock, another moon offers a completely different kind of world. Farther out, orbiting Saturn, lies one of the most Earth-like environments in the solar system, at least in structure. Titan has lakes, rivers, and even rainfall, but not of water. Instead, its surface is shaped by liquid methane and ethane. These hydrocarbons exist as liquids at Titan's extremely low temperatures, creating a weather system that mirrors Earth's water cycle. Methane evaporates, forms clouds, falls as rain, and collects in lakes and seas across the surface. Titan's thick atmosphere and complex chemistry make it one of the most intriguing places to study. It shows that Earth-like processes can occur under completely different conditions, using entirely different substances. Over long stretches of time, even the most familiar relationships in space are slowly changing. The Moon is gradually drifting away from Earth at a rate of about 3.8 centimeters per year. This movement is caused by tidal interactions between the Earth and the Moon. As the Moon's gravity pulls on Earth's oceans, it creates tides that slightly deform the planet. Because Earth rotates faster than the Moon orbits, these tidal bulges are carried slightly ahead of the Moon, transferring energy to it. This energy causes the Moon to move into a higher orbit, slowly increasing the distance between the two bodies. While the change is tiny on a human timescale, over millions of years it becomes significant. In the distant past, the Moon was much closer, appearing larger in the sky and causing stronger tides. This gradual drift shows how gravitational interactions can reshape orbits over time, and while our Moon moves away slowly, other moons in the solar system have far more unusual origins. Orbiting Neptune is a moon that defies the usual patterns of motion Triton. Unlike most large moons, which orbit in the same direction as their planet's rotation, Triton moves in the opposite direction. This is known as a retrograde orbit, and it strongly suggests that Triton did not form alongside Neptune. Instead, scientists believe it was once a separate object from the Kuiper Belt, a distant region filled with icy bodies that was captured by Neptune's gravity. This capture would have been a violent event, likely disrupting any previous moons Neptune may have had. Triton's unusual orbit makes it one of the most interesting moons in the solar system, offering clues about how planets can capture and reshape passing objects. And while Triton's motion is unusual, even our own moon holds hidden activity beneath its surface. Although the moon appears quiet and lifeless, it is not completely inactive. The moon experiences seismic activity known as moonquakes. These quakes can be caused by tidal forces from Earth, temperature changes, or impacts from meteorites. Unlike earthquakes on Earth, which are often brief, moonquakes can last for much longer, sometimes up to an hour. This is because the moon lacks the water and complex internal structure that help dampen vibrations on Earth. As a result, seismic waves can travel through the moon's interior and echo for extended periods. These prolonged vibrations reveal that even seemingly inactive worlds can have dynamic internal processes,